This conference will now be recorded.
A very good morning, afternoon, or evening to one and all present here virtually with me today. Let me introduce myself. My name is Jessica Reeves, Conference Secretariat at Coalesce Research Group LLC, and I will be available for any of your queries or questions throughout the webinar to help you out technically and organize the webinar successfully. For the next 5 minutes, please allow me to give a brief description about our organization, Coalesce Research Group, and also the further instructions. Coalesce Research Group LLC is very delighted to welcome you all the speakers, supporting associations, friends, and delegates present virtually with us today. With the aim, mark the scientific excellence, facilitation, conversation, sharing knowledge, Coalesce Research Group the objective of setting standards in delivering excellence in the research among the researchers, academicians, and industry, promulgating the research through conducting events, online webinars from various fields of science, technology, engineering, and technology, with collaboration have succeeded in creating a platform for developing a strong professional network for people across the world from the respective fields that they haven't connected in a while. As a global scientific event organizer, we plan and carry out international conferences, meetings, seminars, symposiums, workshops, and excellent networking opportunities, conversations leading to innovation, learning new opportunities, lasting working relationships, professionalization with the professional around the global network. Just recently, we have also started our own platform for open access peer-reviewed scholarly literature, where all the content is freely available without charge to the reader. We aim to share new research advances to scientific publications which will help in minimizing the borders and contributing to sense of research work to researchers, research scholars, eminent authors, students, across a broad spectrum of medical, clinical, pharma, and engineering scientific disciplines, and the subspecialties to promote the ideas which will guide the development and facilitate the use of scientific information and ensure its quality, and also the connecting link between the scientific community via community. We are committed in ensuring that our journals are disseminated worldwide, so that the researchers are able to access our content wherever and whenever they need. As being the very few journals, we have some quite interesting journals, and we will be very glad if any of our today's research students or delegates could extend your support by checking the journals and publishing at any of the journals according to your area of expertise. We will also send an email with all the journals after the commencement of the webinar. Do take your time to check the website. Finally, I would like to thank all the attendees and participants of today's webinar, and hope you will enjoy the webinar and take knowledge from the sessions today. Do take your time to check the website. Also hope your participation will contribute to new research findings and that is lead collaboration and initiatives. Before we start with the sessions, I guess some of you will be about your meetings now. Let me just explain you the important. Before we start with the sessions, I guess some of you will be on the GoToMeetings app page. You can find the importance of bottom. My camera screen and on the GoToMeetings app. Is my voice is audible? Is there any problem? My camera screen and on the GoToMeetings app. Is my voice is audible? Is there any problem? My camera screen and
yes, we can hear you with echo.
Is it okay now?
Yes, we can hear you with echo.
Is it okay now?
Yes, we can hear you with echo.
So on the GoToMeetings app web page, you can find 4 icons at the bottom screen. That is mic, camera, screen, and end button. Mic, click on that to mute or unmute yourself. I request you all to stay muted while our speakers are presenting their research work so that it doesn't cause any disturbance to you. camera. You can use this button to share or unshare the web camera. If you have the option to share the webcam, you can do it. Otherwise, it's completely your choice. Screen. You can use this button to share your screen with us. This is the main part of the webinar. During the presentation, after I call your name from my side, I will be making you the presenter. Only I give the permission, you will be able to share your screen with us. So once I make you the presenter, you can click on the screen button and you will get. So once I make you the pop-up window to share your screen. And this is the fourth item where you can use to leave the session. So Kevin, let's not take much of your time. Start our program. So for our today's program, the first present is Dr. from North Universe, Northwest University in China. Dr. Binglin Lee. Are you ready with your presentation?
Yes, for me it's ready, but the voice is not very clear.
Your voice is not audible to us.
Okay.
आपने डिसाइड हो ना तो फिर ये इतना टाइम नहीं वेस्ट होता स्टूडेंट्स हो ना आप लोग इस तरह नेक्स्ट में क्यों नहीं आएगा फर्स्ट टाइम ऐसे ही होता है
How other question, how to share the screen because optional was allowed.
Not able to hear you.
नहीं वो नहीं होगा ये कौन सा था लिनोवो का ये टीचर्स के पास होगा इधर बैठे हैं
Hello. So how to share the screen?
Is Dr. Binglin is audible to anyone?
Yeah.
लिनोवो की हाँ ये लगा मैं फोन ओपन कर दिया
Yes, hello, Dr. Binglin. You are the new presenter now.
हाँ इसमें लगा मुझे पता नहीं क्यों लग रहा है कि मैं लेके आई थी
Hello.
Yeah, hello.
So I can see and I can hear, but I can't share the screen because this whole thing is black.
I have given you the permission to share your screen.
It
Hello, can I know what's the problem is causing?
okay. I try again. Yeah.
Yes, it's visible.
Hello, does it work?
Yes.
Okay. Okay. Hello, everyone. Thanks for your time. It's my honor to have the presentation in this meeting to share my work. My name is Bing Lin. I come from Northwest University, and today I want to introduce a short work in our lab about to develop efficient and green aqueous solid system to produce the phospholidizerine. And first one, I want to introduce the phosphatidizerine. I just called it as a PS because it's easy to call. It is a very crucial component about cell membranes, and it can involved in many signal pathways, so it's very important. And if we can eat it, and it was widely used as a function food or medicine, it can be used to improve the memory or repair damaged nerve cells or treatment about the child's ADHD. The most important case, it can prevent and treat Alzheimer's disease. So it has many functions. Recently is a global PS market analysis. It's from this picture, you can see that PS was widely used as a medicine, foods, function foods, or supplement. And from this is a very normal PS productions. You can buy it in the many shop. So from this picture, we can see that the in the world for the PS there is a huge market. So how to produce, I mean prepare this function compounds? There is many research they focus on this topic. For the phosphatidylserine, I mean the PS, there it has many source. From the different source, they have the different functions. From the research, it found that the PS from the soybeans shows the highest activity, and the next is a bovine. But this one is not a good selection, because bovine will have the risk to transfer the animal diseases. So now bovine PS from bovine were not allowed using the medicine or function food. The soybean should be the best choice, because it's easy to get. So how to prepare this PS? I mean the phosphatidylserine. There is a three method. First one is a physical extractions. However, this PS is very low in the nature. The content about this this phospholipid in the nature is not did not reach 100%, so the content is very low. So if we use a physical extraction, it will consume a lot of the organic solvents and very high prices. Another way is chemical synthesis. The process is very complex, and during this process, the physiologic activity about PS will be lose significantly. So it's not a good selection for the PS preparation. In this side, generally people thinking the enzymatic method should be the best way to prepare the PS. We use an enzyme called phospholipase D. It can catalyze a reaction called transphosphatylation, and use this reaction we can exchange the polar hand group about of the phosphatidylcholine. We call it PC, is our one of substrate, and interact with the alserine and to produce our product PS. And it also has a side reaction we call the hydrolysis about of the PS, and it will be produce a side product. So this is a scheme about how we prepare the PS. First one, the soybeans, it will be manufactured into the soy oil, and after that we can get much okara. Sorry for that, and it will be manufactured into the feed or fertilizer, because it has a very low added value. So we think about a new method. We want to extract the phospholipids from this one and to here, because this one PC has a huge content in the nature, and we use this transphosphorylation by the phospholipase D and convert this one into this one. This is our ARM product with a very high value. And now the reported system can be divided into three parts. First one is traditional biophysics system. Because our substrate phospholipids were not dissolved in the water, so we need to use an organic phase to dissolve these phospholipids, and we put second substrate and our enzyme into the water phase, and we mixed two phases for the reaction. The disadvantage about this system is their selectivity and the activity were very poor, and it used a lot of toxic regions because organic phase generally is ether. So many research want to develop the macro aqueous system. They use a low toxic organic solvent to replace the traditional ether. However, those low toxic organic regions were very expensive, even expensive than our product. It's not a good idea for the industry production. Then people want to develop the aqueous system. They use the immobilized enzyme to mix this immobilized enzyme with PC aggregation in the water, just put them together for the reaction. And they also want to use a existing carrier to disperse the PC aggregation, but the results indicated the PC were always in the formation of the PC aggregation, so the reaction interface is very low, the efficiency is very low, selectivity is also poor. And then people want to use surfactant to form the mixed micelle with phospholipids. It works. It can significantly improve the improve the reaction interface. However, after reaction, the surfactant which has the same chemical and physical property with our phospholipids, so it's very hard to remove from our product. Anyway, the best reaction system should have the high efficiency and easy to operation, and no toxic, no pollution, easy separation. Therefore, we propose one reaction system. We called it as an aqueous solid system. We use the absorption and the precipitation to disperse our substrate. It looks like this. We dissolve our substrate PC into the acetate solution, and we added some existing carrier like silic add to this solution, and we add the acetone which can precipitate our PC in the solution, and we collect this carrier adsorbed PC and put them again into a water solution, and we added the enzyme, we added the second substrate, L3, for the further reaction. Compared, this picture is a traditional biophysics system. This one is our system. From this scheme, we can see that for the traditional systems, the enzyme is always stay in the water, and our substrate stay in the organic phases. So if they want to interact, they need to cross this interface. But in this aqueous solid system, the substrate were always attached on the interface, so they didn't need to cross this interface because they are always in this interface. So reaction efficiency will be improved. And for other phenomena is this one. For the aqueous solid system, there is no organic solvent in the reaction. So there is for the enzyme, it reduces the possibility to the aggregate, because when they contact with the organic solvents, it will make them aggregate. So the activity about this enzyme in the aqueous solid system should be higher than in the biophysics system. Later, we also compare the properties of the different carriers, the surface polar, surface area, and pore channel are three important in fact for these reactions. And from this one, we found that silic should be the best choice, because PC can be dispersed on the surface of the silic in average level for picture B, because the surface about this carrier is the polar is too high. So although there is much PC aggregation, but they didn't like to attach on this carrier. For the picture 3, because their surface area is too low, so it can't when the PC, when our substrate, when we increase the amount of PC, this carrier can't absorb all of them. So much PC aggregation were absorbed. For this picture D, because although it has a large surface area, however, the pore diameter is too small, so much PC can't enter into the pore channel, and much PC aggregation were observed. Then the special attention was paid on the PC coverage, on the pore diameter, surface area, and the yield of PS. From this picture, based on the yield of PS, we can divide this picture into three parts. This is 1, 2, 3. In the first one, in the first part, we can see that with the increase of PC coverage, the yield of PS didn't decrease. And into the part 2, it decreased significantly. It's because the pore diameter about these carriers decreased due to the absorption of PC molecular. So when the pore diameter decreased to 7 nanometers, the substrate PC can't freely enter into their pore channel, so the mass transfer resistance can't be avoided in this stage. So the yield of the PS decreased. And we also compared our system with reported system. From this picture, you can see that the selectivity and the activity about this reaction was improved significantly. And we also studied the reuse of this system, because in this system we didn't the enzyme didn't contact with organic solvents, so the stability about this enzyme in water is better than the biophysics systems. Next, we are thinking about to avoid the use of the organic solvents in the whole reaction process. So we modified the silic. We prepare a very special modified silic, and we found this modified silic can absorb the PC in the purely aqueous aqueous solution. In this solution, the formation of PC is aggregation, but this silic can absorb all of this PC aggregation. And after absorption, we put enzyme in and we put another substrate, and it can carry on the reaction. The preparation process is like this one. We bound the treating X100 on the surface of silicon. Next, we prepare for different silic with different size, and we study the content about the treating X100 on the surface about carriers, and we found that in this picture. This picture is very interesting. We add 1 milligram PC into the water, and this one we use a normal silic, and for this one we use the modified silic. From this picture, we can see that after absorption, because this one is a reference, it's not clear. For this one, the normal silicon is also not clear, but for this one, the edge of the nitrogen is very clear to observe. It's because carriers were precipitated, and so the solution is very clear. So after the precipitate, after several time, we measure the solution and test the PC content in this solution. We found most PC were absorbed on our modified silic in here. Okay. And then we pick we collect those carrier absorbed PC and add some enzyme, add some alcyrin second substrate for the transphosphorylation, and we found it can work well. The highest yield of PS can reach 99, close to 100%. So next we start the adsorption model. We use the two models to study this adsorption process. One is one-step model. It means hemimicelle was formed in one step, and we also use a two-step model, and we calculate the relevant parameters. From this picture, the most interesting thing is this one. The Gibbs free energy of the formation of micelle is a positive value, but that of hemicelle is a negative value. It means the PC aggregation in the solution would like to absorbed on the carrier, not dissolved or form the micelle in the water. So we prove this process is a spontaneous process. Next, we think about that if treating X100 can attract our substrate, the protein also have many hydrophobic function group on its side surface. Maybe there is a possibility for this protein. They can also attract our substrate in the water solution. So we start the immobilized phospholipase D. We just called it for immobilized PLD, the enzyme name, and we studied the protein coverage on the immobilized enzyme and studied their adsorption ability and catalytic ability. And we found a very important point. In this point, the protein coverage is very low, but it can efficiently absorb the PC aggregation in the water. We will explain this phenomenon in the next slide. For this absorption process, we want to study which adsorption driver force is, where the driver force come from. For the protein, it should consist of two parts. One is from activity site, because this enzyme can can interact with this substrate, so it has a selectivity interaction with this substrate. Another way, on the side surface of this protein, there is a much hydrophobic group. It should have the no selectivity attraction for this substrate. So we're hitting from this picture, we're hitting this protein to denature this protein, and then we use the same method to immobilize this protein as the same way, and we compare the adsorption ability between the immobilized PLD with or without not denaturation, and the results indicated there is no difference. So we use a dynamic simulation, this picture B. We use a dynamic simulation to denature this protein, and we use a docking to study this protein. We found that after denaturation, no substrate can end into the pocket. I mean the activity center, but this protein can also provide much bonding position on the side surface, and we also calculate the number of this position. This is 20. This is sorry. This is 18. This one is 19. So there is not significant difference. So we think the adsorption driver force should come from the side surface. It's controlled by the hydrophobic interaction from the no selectivity interaction. Now, it also explains a phenomenon why the high content is not good for the adsorption, because adsorption is carried on this surface. If the content of protein in the carrier is too high, the distance between each protein is too close, so the PC can't end into the side surface. Next, we want to explain, because we want to explain how the transphosphorylation can carry on, because our enzyme is immobilized on the carrying, and our substrate is adsorbed on the protein. So our enzyme and substrate are all fixed. How those fixed substrate and enzyme can react? So we use a dynamic simulation to simulate this process, and we found for the substrate for PC, it has 4 ways to end into the active center. The gray region is active center. First one is substrate can directly diffused into the active center. It's very easy to understand. It's directly end into here and participate into the reaction. But in most cases, they can't directly end into this pocket. They are absorbed on the other regions, like here, 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 or here. And they also have the 3 ways to end into this pocket. First one, they will use a rapid adsorption and desorption, like this. The adsorption and desorption is a very rapid process, and use this way they can change their location until they end into the pocket. And for other one is like this one, they attach on the surface of protein and they will show a tendency of parallel movement on the surface of protein, like they roll on the surface of the protein and into the active center. But for the most case, they are a combination pathway. They absorption and desorption, and they also roll on the surface of protein and into this pocket. And this dynamic simulation explains well why this reaction can be work. Finally, we also test the stability about this system, and because we use water to replace the traditional organics. I mean the ether. The stability of the water is better, so the optimal reaction temperature was increased. Oh, sorry. Was increased. It will increase the reaction efficiency, and after reaction, we use the coconut oil to extract our product to avoid the use about toxic organic solvents and manufacturing into the microcapsules and something like this. And because this is an immobilized enzyme, we can also reuse this enzyme very easy by the separation, and it also shows good results. Finally, I want to thank all the institutions who have support us or have the cooperation with us, and I also want to thank all the research working in our lab, and this is my email. If you have any question or if you want to have the cooperation in the future, please be free to contact with me. That's all. Thank you.
Thank you, Dr. Binglin Lee, for your presentation. Is anyone having any questions? Okay, no questions from anyone. Moving on to our next presenter is Dr. Gang Zhu from China, but he has not yet joined. So we will move on to next presenter, that is Dr. Chun Hu Lam from City University of Hong Kong, Hong Kong. Hello, Dr. Chun Hu. Are you ready with your presentation?
How to close this screen share?
You can close the screen sharing option.
Okay, I need to close off them, I think.
Yeah, hello, Dr. Chun Hu.
Hello. Hi.
Yeah, hi.
Am I presenting now?
Yes.
Is it my turn?
Yes,
Oh, okay.
as the previous speaker. Yes. Okay. I'm making you the presenter now. Just a minute.
Okay. Sure. Can you just give me one moment? Let me just pick up my presentation.
Yes.
Ah.
Now you are the presenter. You can share your screen with us.
Sure.
Yes, it's visible. You can start your presentation.
Thank you. Okay. Can you still see it?
Yes, yes.
Terrific. Sorry, this is the first time I'm using this software. Just give me one moment.
Okay.
Okay, got it. Okay. Okay, I'm going to start now.
Yes,
So
yes,
thank you everyone for attending my talk. So my talk today is going to be about electrocatalytic transformation of biomass for chemicals and fuel production. as climate change mitigation strategies. I'm Dr. Jason Lam. I am an assistant professor at the School of Energy and Environment at the City University of Hong Kong. So thank you for organizing this webinar, and it's my pleasure to share my work with you today. So my talk here today is mainly going to focus on why it is important, essential to upgrade biomass into commodity products like biofuel. And I'm going to show you one of my major research interests is electrocatalysis. So we are going to see how we can use electrocatalytic method to upgrade biomass into a renewable fuel precursor so that we can alleviate or reduce our dependence on petroleum resources. So why is electrocatalytic essential in the process of transforming biomass into a fuel precursor? Well, if you take a look at this biomass, very general representation, biomass consists of three major components, which is cellulose, lignin, and hemicellulose. So these are all major components of biomass, and depending on how you look at it, they mainly can break down from very aliphatic components such as cellulose and hemicellulose, and lignin, which is consists of aromatic portion. But all of this biomass add up together provides us a very important source of renewable carbon that we can make into either fuel or chemicals depending on our need. However, biomass itself, although very abundant, they intrinsically have a very low energy value. On average, biomass has about 16 to 19 megajoules of energy per kilogram. And just to give you a point of reference, gasoline, the fuel that we drive in our car, that we used to drive with in our car, has about 43 to 45 megajoules per kilogram. So we can see the vast differences of the energy content between biomass and gasoline that makes biomass has to be further upgraded before we can even consider it as a fuel precursor. And that's exactly the background and motivation of my work, is that I'm asking the question of how we can use electrocatalytic method to transform this energy diluted biomass into this energy intensive gasoline, and how we're going to use electrocatalysis to carry out such task. So why electrocatalysis? Well, one of the work that I conducted the experimental lab work of electrocatalytic upgrading is that I actually did a project on the life cycle and technological economic assessment of how feasible to use biomass to conduct this work. So what we did was we compared the bioethanol, the amount of energy we can get if we transform all the biomass into ethanol in the process, and compared our proposed method of transforming biomass using an electrocatalytic method, and the results were quite staggering. So let me just walk you through the whole process here. Now, imagine so looking at the energy consumption in the United States transportation industry, that each year they use in the United States use approximately 29 exajoules of energy per year. And then naturally, we're going to ask, so how much energy can we get from non-food grade biomass here? Well, the answer is quite concerning, because we can only get about 20.6 exajoules per year, which is only about 2/3 of what the energy was spent in the transportation sector alone. So if all of this non-food grade biomass energy is being used to ferment into ethanol, what would the result be? Well, it turns out we ferment all of this dry biomass into ethanol. The amount of energy that is available to this route is only about 9.1 exajoules per year. Well, it's far lower than what is available. It's almost only half as much. And that's because fermentation discards approximately 33% of the carbon during the process, and this carbon could have been a very valuable building block for us to make fuel. Also, bacteria themselves required all of this biomass energy to sustain their operation. So in other words, we're actually using some of this bioenergy to convert ethanol, to convert biomass into ethanol. So this is not exactly energetically favorable reaction. I mean, even though it's cheap, we are actually paying a huge price in energy for this process to happen, and the resulting is a dramatic reduction of energy, in this process, as you can see here. So this is the Sankey diagram that we did to analyze the amount of energy that we would have gotten if we are fermenting biomass into ethanol instead. So what we're proposing here is called a pyrolysis plus electrocatalytic upgrading method. And in this case, the scenario is much more optimistic by comparison. It's still not ideal, but it's far better. And that is because when we pyrolyze biomass, we are transforming more than almost 70% of the carbon in the process, and we are able to install extra energy into the resulting biofuel, the liquid product of the pyrolysis product. And the way it works is that we are pyrolyzing this biomass into a liquid called bio-oil, and we're going to use electrocatalysis catalytic method to install extra energy into this bio-oil as chemical bond. So as a result, you can see there's an energy booster in this area here, and allow us to upgrade the amount of energy that was originally missing the biomass. And one of the advantages in this method, in addition to it allows us to use electrocatalysis to upgrade it, is that pyrolysis can also allow us to self-sustain the model, because any combustible gas that's generated process can be back feedback into the pyrolyzer, allowing us to self-sustain the pyrolysis process to generate more bio-oil or other biofuel, depending on or other biogas, depending on need. So that's exactly why I'm very interested in this project, is because we are seeing a very promising route to use this biomass that allow us to couple the renewable energy we can harness from, say, solar panels or wind turbine. So what can we do with this biorefinery waste, or all this biomass available from agricultural sector or any other yard waste, or all this kind of biomass related waste? So as I was saying, the method that we're proposing in this case is called fast pyrolysis, where we take biomass, we basically subject the biomass, dry biomass, into a condition to heat it up rapidly in the absence of oxygen. This interesting condition basically would decompose the biomass, or liquefy it, if you will, and turn this biomass into what we call bio-oil. And some of the products are going to become biochar, which is a solid, and we're going to form a little bit of the biogas as well. And this number could be changed depending on what we call the residence time, how much the biomass subjected to this pyrolysis process. But overall, in the optimized condition, we are looking at approximately about 70% of the biomass carbon being transformed into bio-oil. There's already some commercial application in the process, but still it's being hindered. Large-scale commercial applications still being hindered by the general understanding of the pyrolysis chemistry, and more importantly, bio-oil right now is considered rather chemically unstable, and that's exactly why electrocatalysis is needed for the process, as you will see in the next few slides. So let's take a look at the general property of this bio-oil. So what we did here with our collaborators in Michigan State is that we took a variety of biomass here, and then we subjected pyrolysis condition. As you can see here, that the bio-oil energy value about consistently hit around 80 to 20% ish, 20 megajoules per kilogram ish, and some was more than other depending on the actual biomass structure. But one of the problems with bio-oil is that it's highly unstable, and that is because bio-oil itself comes with a lot of acidic acid content. It's very corrosive, so because of all this acidic acid, and it's also because it has a lot of aldehydes and ketones. And these carbonyl groups, coupled with the presence of acetic acid, is going to generate a lot of condensation problem, and causing the biomass to, bio-oil to polymerize very quickly, even at room temperature. So that trigger a storage problem for bio oil, and which is one of the major reasons why bio oil it's not a very favorable thing to work with as of today's technology. Moreover, bio oil also itself has a lot of water content, about 15 to 13%, but that's because biomass itself has a lot of oxygen inside it, and so during the fast pyrolysis process, biomass is inevitably will form quite a bit of water into the resulting bio oil product. So what do we need to do in order to turn this bio oil into something that we can use as a fuel? Well, let's take a look at some of the general fuel properties. Well, to become a fuel, it needs to be it has a neutral pH, chemically stable, and most important of all, high energy content, about 45 megajoules per kilogram, as we saw earlier, and also no water content. And interestingly, most of these problems can actually be solved by electrocatalysis, as we're going to see in this presentation. Also, just to give you a quick GC analysis of what the bio oil composition looks like. This is the bio oil composition that we got from pyrolyzing switchgrass at 500 degrees Celsius. As you can see here, we're getting substantial amount of acetic acid because of the, as I was saying, because of the a lot of the cellulose content, but we're also getting a lot of these aromatic components resulting in lignin degradations. As you may know, lignin from biomass is basically a big sheet of three-dimensional aromatic polymer. It provides a structural integrity for biomass. It's very difficult to break down, but in pyrolysis process, it breaks down quite readily, and it gives us the aromatic compound that we need. And so these are the compounds that we're trying to target at, because they naturally already have quite a bit of energy value inside of them. So anyway, this GC mass spectrum gives you some general idea of the complexity of the biomass, showing you the presence of these rich aromatic molecules ready to be upgraded. At the same time, we're also seeing a whole abundance of this aliphatic aldehyde that is readily condensable if they are not hydrogenated. So if this double bond persistently appears in bio oil, we could get quite a bit of condensation happening. So what are we doing with this project specifically? So what I've told you so far is that we're trying to pyrolyze these biomass and get a bunch of liquid product called bio oil, about approximately 70% of the accounting for 70% of the carbon content. 15% could be biogas, and the other 15% could be biochar. So this project is about we're taking this bio oil, which is chemically unstable because of all of these aldehydes and aromatic substrates. We're using electrocatalysis to perform some upgrading and to try to get the biogas, turn the biomass into gasoline from the process. The interesting aspect of this method is that we're taking biomass, which is very good at capturing carbon dioxide, but bad at capturing light energy, which is only like 1% efficient, and we're coupling this with things like solar panel per se, which cannot capture carbon dioxide, but at the same time, it's very good at capturing light energy, 10%. So we're basically using electrocatalysis as a bridge to link up these two interesting quote-unquote technology. So biomass can help us capture carbon, bad at capturing light, but now we have a solar panel which cannot capture carbon, but it captures light efficiently. So we efficiently marrying the two technology together using electrocatalysis and trying to turn this bio oil into something we can use to make gasoline. So in terms of the chemistry, what do we expect, and like why hydrogenations or any other chemistry would happen? So in order to convert biomass or bio oil into a fuel precursor, we're talking about an energy upgrading process. So in order to upgrade the energy content of any molecule, we have to do two things. One, we have to put in more hydrogen into this, and two, which is more important thing, get rid of any oxygen inside the molecule. And that is because during the combustion of the reactions, any oxygens inside the molecule does not add fuel value to the heat of combustion. So in other words, oxygen in the molecules only add weight, but not the fuel value for the compound. Therefore, this whole task about electrocatalysis is about transforming all of these oxygenated aromatic compounds or any other oxygenated compound you find in bio-oil, hydrogenate them, or even better yet, deoxygenate it. Because if you take, so give you an example about this process. Let's say glycol, which is a fairly abundant molecule you find in bio-oil. You take this, and if you hydrogenate this and you deoxygenate this compound, you will successfully upgrade the energy content of this molecule because you cut off this methoxy bond, this methoxy group. You effectively increase the energy content by 20% because as a result of this deoxygenation when you get phenol. And when you hydrogenate this phenol molecule to get cyclohexanol, you effectively increase the energy content by another 7%. It's not as much as cutting off an oxygen, but it's a step in the right direction. If you manage to achieve dehydrations to cut off this carbon, alcohol groups, then you will get a cyclohexene, which is another almost 20% boost in energy content. And finally, if you hydrogenate the last double bond here, you get another 2% extra energy, and you reach about 46 megajoules per kilogram, which is what we consider as gasoline level. So this model compound this illustration tells you the importance of why hydrogenation and deoxygenation is very important in the process of upgrading bio-oil or any biomass derived compound into more like a fuel-like compounds. Okay, so now into the chemistry part of my project is that, so what we did here was that we developed a system, like very simple electrochemical system to allow us to perform electrochemical hydrogenation of glycol into selectively into cyclohexanol. And some of the highlights of this project is that first of all, the entire system runs at 75 degrees Celsius, which is below water boiling temperature, 1 atmospheric pressure, so we don't need any pressurizing system, at pH 8, which is very mild. The cathode, which is the core components of this hydrogenation, is made of a porous nickel catalyst, and it is heterogeneous. It's very convenient to use. Highlight number 2 is that the hydrogen that was used to supply the electrocatalytic hydrogenation comes from water oxidation on the anode component. And we purposely chose an anodic catalyst, which was cobalt phosphate at that point, to perform this water oxidation for us to generate the hydrogens that we need. So overall speaking, the system runs at a very mild environment and does not require any precious metal. And in terms of chemistry, the most interesting aspect of this work is that the glycol actually undergoes a very selective demethoxylation in the process to yield phenol, which then go through a hydrogenation to yield cyclohexanol. Because this is completely contrast to our general understanding of organic chemistry that would have taught us that the plain hydrogenation of the ring to form 2-methoxy cyclohexanol instead. But no, instead of doing this, it actually goes through the methylation and then it yields phenol and then go to cyclohexanol. So from a fuel chemistry standpoint, this is actually very advantageous because as I was showing you in the last slide, anytime that we cut off this carbon oxygen bond, it will be advantageous for us to make a more fuel valuable component. So this selectivity actually works in our favor, and it actually was very selective in the process. We get almost over 99% selectivity in this case. So because of this very high selectivities chemistry, and it also works in a very mild environment, so this really triggered us to study the reaction further. and see how we can apply this similar system, this particular selectivity into a comparative model in any other biomass model compound. So what we did here is that we are trying to subject this other similar compounds into the same environment and see how they would react. So what we did was we first, we do the 2-methoxy group as I showed you last slide, and of course the selectivity was very high. We get almost exclusively cyclohexanol with no clean hydrogenated product. We get very nice the methoxylated product. When the alkoxy group, the side chain increased, it becomes into ethoxy group. We also observe a similar very pleasant selectivities. And likewise, when it becomes isopropanol, again, we observe similar impressive selectivity as well. So anytime we have a methoxy group on a 2 position, we observe this very superb and amazing selectivity in the process. However, if the methoxy group is on the 3rd and 4th position, we no longer observe this amazing selectivity. We observe some of the plain hydrogenated product, 3 and 4 methoxy cyclohexanol, and selectivity drops from almost 99% to about 50% per se. So clearly there's something going on with the unique aspect of having the 2 group adjacent to another. So knowing this interesting selectivity issues here, we decided to propose a couple of working model to explain why that might be the case. And so long story short here, what we discover in this case is that the methoxy groups and the alcohol group on the glycol are actually having this coordinated relationship such that it promotes elimination reactions after the hydrogenation reaction. Excuse me. So what happened? The first step here is that we are seeing a partial hydrogenation of this glycol and yielding us a partially hydrogenated molecule in this case. And then because of the coordination between the hydroxy group and the methoxy groups here allow us to facilitate this elimination such that we could produce a phenol molecule, and this phenol molecule would reabsorb on the catalyst surface and then become hydrogenated. You use cyclohexanol instead. So because of this coordination, this allows us to have a very selective process. It often almost 99% of the methoxylation happens. Whereas if the methoxy groups and the hydroxy group are further away, this whole coordination no longer happens. We are left with a much lower selectivity, about 50%. Still something to happen, but it's far less impressive. So then we were curious whether this system, this interesting selectivity, is also applicable to other biomass related compound. So what you're seeing here, this is molecules called syringol, and you probably have already can notice this is an extraordinary, very similar to what the glycol is. The only difference between two is because the extra methoxy group. Syringol is also a model compound or a compound that we observe frequently from biomass fast pyrolysis. In fact, some of the wooden feedstock lignin also have syringol functional groups here. So we wanted to try see syringol could also benefit from this chemistry, and to our delight, it also worked on syringol. So what we observe here is syringol actually yield glycol and then yield phenol and then yield cyclohexanol. And in the process of doing so, it does not yield any methoxy cyclohexanol or 2,5 dimethoxy cyclohexanol. So this interesting demethoxylation process is also applicable to other biomass compound observable from biomass degradations. So this is a kinetic diagram that we did and showing you the growth of cyclohexanol and at the expense of glycol and the phenol, which was the key intermediate of the process. So with this technology, this is the big picture that we're trying to propose to how we can maximize the value of bio oil and how we could use this bio oil to promote a larger biorefinery pictures. So as you can see in this picture here, what we're trying to show is that the biomass could be harvested locally in this case, and then it goes through a local pyrolysis process to turn them bio oil, and and then you can go through immediately upgrade process to using the locally harnessed electricity. And then after upgrading, these upgraded bio oil can be stored or being transported into other central refinery location to be made into fuel or other chemical compound. Now, the reason why we're proposing this delocalized biomass processing strategy is because when this converted locally, we can save ourselves a lot of energy from transporting the biomass around from one place to another. As I was saying in the very beginning, the biomass itself has a very low energy content compared to ordinary gasoline. So bringing it around from one place to another is actually energetically unfeasible. And the goal here is to upgrade the bio oil first, turn into bio oil first, upgrading regionally using the renewable electricity. Then when we need to transport them later for further upgrading, it will much more energetically feasible. And then we can enjoy this carbon neutral renewable fuel. Okay, so in summary, today I've talked about a reaction about this electrocatalytic hydrogenations. The reaction works in a very mild environment. It works at 75 degrees Celsius, 1 atmospheric pressure, a very mild pH, and it's very mild compared to conventional hydrothermal upgrading condition, which usually works at about 200 to 300 degrees Celsius and a very, very pressurized environment. And the whole thing works is because the electrocatalysis has a unique property that allows us to generate a lot of absorbed hydrogen with just a little bit of potential or current density, if you will, about 10 milliamp per centimeter square, which is a very low current density, require a very low voltage input. We can already generate almost 100 bars of absorbed hydrogen on a catalyst surface. So that could immediately strike the contrast between how mild electrocatalytic method is compared to conventional hydrothermal method. And we also discussed the mechanisms of glycol, how that can be turned to cyclohexanol, which is a much more stable and energetically valuable molecules for fuel production purposes. We talked a little bit about how this electrochemistry could promote the oxygenating mechanism and show a little bit of kinetic studies. Lastly, I want to thank you for your attention. If you have any questions, feel free to send me an email. I can be reached by jason.lam@ctu.edu.hk. I want to also thank Professor Ned Jackson and Professor Christopher Saffron from Michigan State, and also provide all of this valuable pyrolysis information, and then some of the electrocatalytic work as well. We did a lot of work together. Also, Professor Paul Anastas and his group at Yale University also provide some valuable input to some of our projects. So my other research interests are also very biomass oriented. So in addition to electrocatalysis, I also work on a little bit of photocatalytic work and trying to look at how biomass could be made into other platform chemicals or fuel or other environmental remediation processes. And I'm also interested in looking at some of the porous material for aerobic catalysis as well. So if you have any research interest in those areas, feel free to send me an email. I'm always looking for additional collaboration opportunities. Last but not least, recently my groups have published a life cycle and technological assessment paper on the work that we just discussed, how biofuel and some of the biomass waste processing could be beneficial to mitigate climate change and benefit the social development and promote more renewable fuel usages. And if you're interested in seeing what are the quantitative support to justify our need for biomass, biofuel renewable chemicals, feel free to look at this paper that we recently published, very exciting. And if you are more interested in the chemistry or the mechanistic aspect of some of the biomass transformation work, feel free to check out one of the recent review that we published of how we transform lignin into renewable fuel and chemicals. So with that, I want to thank you for your attention. And if you have any questions, feel free to ask. And I would love to, answer any questions that you may have. So thank you.
Thank you, Dr. Jason, for your presentation. Is anyone having any questions? Okay, no questions. Thank you once again for your presence and presentation.
Thank you.
Okay, so our next presenter is Dr. Jordi Poater from University de Barcelona, Spain. Hello, Dr. Jordi. Are you ready with your presentation?
Yes, I'm ready with my presentation.
Yes, I'm going to make you the presenter. Yes, you can share your screen with us.
Let me. I have to restart. It doesn't allow me to. 1 second.
Okay.
Yes, now I'm ready. Do you see the presentation?
Yes, yes.
Okay, I'm a star. Thank you for your kind invitation to this meeting on catalysis. The idea is to show you how iron catalyst can also mimic the behavior of palladium, very well-known catalyst in cross-cupping reactions. This will be the scope of my presentation.
Hello, doctor. I'm sorry for the interruption.
Sorry?
There is no presentation. We are seeing like a white screen. With the presentation now, it's not. Yes, perfect.
There must.
Yes, yes. Now it's visible.
Okay, sorry. So I will start with. You do know the story of palladium-based catalysts, which have already been given several Nobel prizes. Here you can see the palladium catalyst cycle that is well known to most of you, I would say. Which is less known is the chemistry of iron, which have a series of advantages, but at the same time, it have a series of disadvantages. We do know that catalyst is ubiquitous in modern synthetic and industrial chemistry and plays a key role in reducing the consumption of energy and feedstocks. However, we must have in mind that designing this catalyst with the desired activity and selectivity is still a difficult task, and it's mainly based through the trial and error most of the times. So my work will be based on the activation strain model that I'm gonna define in a few minutes. And the idea is to use it to understand how and why a certain combination of a metal center, the ligands, and the solvent is able to selectively catalyze one particular bond in the substrate. So I want to explore the potential of iron to take over from palladium in classical closed shell catalytic cross-clapping reactions like the cycle that you see here. So the idea is to teach iron how to perform. with a more systematic development of iron-based cross-clapping chemistry and the corresponding catalyst. So cross-clapping reactions constitute one of the most important reactions to create a new bond between two carbon atoms. And it has been the basis of several studies, both experimentally or computationally, like the one that I'm introducing right now. As you know, the first and rate determining step in this catalytic cycle is the activation of the bond, such as the carbon-hydrogen, carbon-carbon, or carbon-halogen by oxidative addition to a transition metal complex. The growing concern about environmental damage and energy consumption is the one that has made us think about substituting palladium by iron. However, its applicability in synthesis is still quite scarce, and the mechanism of iron-catalyzed cross-cutting reactions is not fully understood yet compared to palladium. So we want to explore a different idea. As opposed to developing a separate and different iron chemistry, the question is it possible to teach iron to do the tricks of palladium? So based on this quantum chemical proof of concept, we have to answer several questions that are the ones will be addressed in this study, and we have systematically explored different iron-mediated CX bond activations for this purpose. So the activation strain analysis. Here we have the cycle that I'm going to refer. And this is the approach I'm going to use. So I'm going to use the iron catalyst with carboxide and analyze the CH activation, CCl activation with chloromethane, and CC activation based on ethane, and compare it to a standard palladium catalyst for the same reaction. I've already referred to the activation strain model analysis, which was developed in our group in Amsterdam in the beginning and right now, and continued since I'm in Barcelona. This activation strain model of chemical reactivity is a fragment-based approach to understand the energy profile of a chemical process and to explain it in terms of the original reactants. This allows an easy assessment of the influence of geometrical and the electronic structure of the catalyst and the substrate. In this work, our main interest is the interplay between one fragment, which is the catalyst, and the other fragment, which is the substrate. The interaction energy, so we have the strain energy, which is the deformation energy to prepare these two fragments that I've just referred, and the interaction energy, which is how these already deformed fragments interact. This interaction energy can be further decomposed into the classical electrostatic interaction, Pauli repulsion between occupied orbitals, which is referred to the steric repulsion, and the orbital interaction that takes into account donor-acceptor interactions between the two fragments, as well as polarization inside the same fragment. So let's go on. Let's start with the different iron model catalysts taken into account. Here I'm comparing the singlet one with the triplet one, and explore the different activation of the C hydrogen, C carbon, and C Cl bonds via oxidative addition. However, before these are the frontier molecular orbitals of this neutral catalyst and their occupation in the singlet and the triplet state. The triplet state is the ground state, however, is only also 2 kcal per mole lower in energy. So we are mainly interested in the iron's less common closed shell chemistry on the singlet potential energy surface. And in this case, I'm going to focus on the singlet state. Importantly, while the palladium D10 metal complex, while the anionic D10 metal complex of this is tetraederally coordinated, the neutral ones, both singlet and triplet, have a C2b symmetry. And the larger axial and equatorial angles, the bite angles, make this system resemble a trigonal bite pyramid, allowing a back and side. We will see afterwards that this is responsible of the less destabilizing activation strain and lower barrier, but I'm gonna enter into more detail in the coming slide. So first I'm gonna show you some kind of proof of concept character of this study, because I'm based on the selectivity determining step of the CX activation, but not only this step, but I'm gonna focus first on this reaction for the whole cycle. So I want to explore the full catalytic cycle for this representative model cross-clapping reaction for both comparing iron at the top and palladium at the bottom, as you can see in here in the slides. Well, it's the cross-clapping of chloromethane with the green art region, metal magnesium chloride, leading to the formation of ethane catalyzed by both the iron catalyst as well as the palladium catalyst, as you can see here in the reactions that you have seen. This will allow the physical factors governing their activity and selectivity to be directly compared and understood. So we have computationally modeled these key steps, which are the first oxidative addition, then the transmetallation, and finally the reductive elimination. The overall potential surfaces of catalytic cycles involving these two catalysts, you can see that are very similar. I mean, if you compare the shape and the different steps, the stationary points, you will see that they are very similar. The most important difference is the rate determining step, which for the palladium is the oxidative addition. However, for the iron catalyst is the reductive elimination step. And which is really unexpected is that the iron catalyst has a 10 kcal per mole lower barrier than the palladium in the oxidative addition step, something that will be afterwards also analyzed with more detail. So based on this comparison, we can justify that the use of our generic catalyst is justified and is a useful tool to understand the fundamental differences between iron and palladium model catalysts. Let's go on to our analysis. Here I have the table with the comparison of the different catalyses that I've analyzed, the iron ones at the top and the palladium ones at the bottom. I don't want you to go into detail into the different values of this table because it's quite exhausting at a certain moment, but you can already see the barriers and compare them. So this is the aim of the present work, is to design iron-based catalysts that are as closely as possible mimic the mechanism of bond activation for cross-clapping as performed by the palladium catalyst. That's why we have taken these 3 bond activations, and here you can see all the stationary points. Let's go to the figure in which you can better see the differences. The oxidative insertions of the iron complexes start from a weakly bound reactant complex, as you can see here, in which the CH3X, let's say, bond coordinates via this CX bond to the iron center. Proceeding from the reactant complex, the catalyst approaches the CX bond, which elongates as we approach the transition state. This transition state is triangular unique, involving partially formed iron carbon and iron X bonds and a partially broken CX bond. In all cases, the lowest barriers occur for the neutral singlet complex iron catalyst. Importantly, these transition state geometries for the iron, both the singlet and the triplet are quite similar. However, the first one, the values of these barriers are much smaller, as you can see here, as well as in the previous table. And we will see that this is associated with a more destabilizing catalyst strain associated with the necessity of a larger widening of the initially smaller bite angle that I've just referred in the beginning of the talk. So, and finally, also this neutral catalyst leads to a more stable product, which is in all cases is a direct insertion of in which the CX bond has been reduced and broken, and these reaction energies are smaller than the ones compared to either the triplet or the dianionic iron catalysis. So in conclusion, based on this, we can say that kinetically and thermodynamically, the most favorable pathways proceed via this oxidative addition on the singlet state energy surfaces, and this will be the main focus of our discussion. Here I can show you briefly the different geometries that I've just referred. So first I have the reactant complex. This is the neutral iron catalyst, singlet state, the reactant complex for CH, CCl, and CC bond activations. Here I have the transition stage with a triangular shape, and finally the right column corresponds to the products. And in this case, we can compare them to this closer bite angle and the consequent strain energy caused by these closer angles for the triplet state, as well as for the dianionic singlet states. So can I understand these differences? The answer is yes. How? So by means of the activation strain analysis. So with this analysis, we analyze the origin and the trends in the reactivity and selectivity for this oxidative addition, and also refer to the corresponding molecular orbital analysis. As we have seen in the previous table, as well as in the previous graphic, the reaction barrier increases from the carbon-hydrogen to the carbon-halogen activation because of a weaker catalyst-substrate interaction, whereas the increase from carbon chloride to carbon-carbon activation is due to an increase in the destabilization activation strain, as just mentioned, referring to the angle. These trends are very similar to those already discussed for palladium in previous works, but allow us to clearly justify the reason why the triplet and the dianionic are not viable, are not active, and for this and are not active candidates for such oxidative step. Which is the main differences? So the height strain that I just referred comes from the iron complex, which occurs because the complexes are near tetrahedral and lack an open site to dock this incoming substrate. And finally, also referring to this bending of the bite angle to make room for the approaching substrate is really crucial to avoid otherwise even a stronger stereo repulsion between the catalyst and the substrate. This barrier for the singlet catalyst increases from 10 to 25 to 48 from C hydrogen, chloride, and carbon-carbon activations. And it's because of two factors. The first factor is the delay in the interaction curve. As we can see in the first graph here at the top left, there's a delay for the CCl and CC bond activations. And the second factor is the higher strain curve of the CC compared to the CCl activation. This elongation, eventual breaking of the covalent CX bond is the main source of the strain energy, while the bending of the bite angle contributes only a little if we compare the different strain contributions. So let's go further to the molecular orbital analysis. And here we can see a basic interaction pattern, which consists of two main features, let's say. In the first case, we have back donation from the d pi of the iron to the sigma CX star of the substrate. And on the other hand, we have the donation from the sigma CX of the substrate to the d sigma orbital of the iron catalyst. This bonding mechanism is the one that you can see here at the figure for the neutral singlet iron catalyst. This catalyst substrate bonding analysis at the transition state show how the destabilizing and electrostatic and orbital interaction contributions to the interaction energy are of comparable magnitude, as you can see in the next table. This is even more crowded. I don't want you to really see the main the values, but at least to be conscious that this ASM analysis allows a deep detail of what's going on in this case. Which is the main difference? Is due to the different HOMO and LUMO of the three substrates. In the first case, we have the in-phase and the out-of-phase combination of the orbitals between the CH3 and the X unit. And these sigma CX and sigma CX star orbitals of the CCl and CCr bonds have one additional nodal surface on the X moiety as compared to the other ones of the CX bond, C hydrogen bond, sorry. This results in a poor catalyst substrate orbital overlap, and thus we have a less stabilizing pi back donation and sigma donation for CCl and CC activation compared to the C hydrogen activation. And this is the reason of the delay of the interaction energy curve that I've just mentioned before. Just for completeness, let's compare the geometries and the interaction between iron and catalyst. So we turn out to our initial question: is it possible to teach iron to do the tricks of palladium? The answer is yes. As we have already seen, the neutral singlet iron catalyst can activate the CX bonds to an extent very similar to the palladium complexes. We have seen that they are even more reactive toward this CX activation, and well, we can see, and we have seen based on the activation strain model analysis, that the main differences are not due to the strain energy, which in these cases are almost the same, but are due to the interaction energies, as you can see in these three graphics for the different C hydrogen, carbon chloride, and carbon-carbon bond activations. If it's due to the interaction energy, we can go further and to check the reason of these differences. And the main differences, again, is due to the sigma donation and pi back donation. Apparently, they should be similar, but we have to have in mind that we have a D10 and a D8 metal systems. Here we can see that referring to these differences, and here we have the corresponding molecular orbital diagrams analysis, which allows an important differences that I've just mentioned. Because of the saturated D10 shell and high energy as orbitals of the palladium complexes, pi back donation is usually the determining interaction. However, the employment of ligands that can push up these palladium d orbitals, like different sigma donating ligands, can reduce this orbital energy gap. This approach, however, differs if one wishes to tune iron D8 catalysts. Here one has to consider both pi back donation and sigma donation from the substrate at the same time. So just to conclude, I've tried to convince you that the closed-shelled iron D8 complexes are excellent candidates for replacing the more classical palladium D10 catalyst in catalytic cross-clapping reactions. We have based our analysis on a proof of concept quantum chemical investigation, which shows that a simple model system like our iron CO4 has access to non-radical pathways for this CH activation and mimic the oxidative addition pathways. The full catalytic cycle of this cross-clapping with the greenite region, methyl magnesium, also catalyzed by our model, exhibit very similar qualitative features, and this allows us to use this catalyst. Afterwards, we have shown that this iron catalyst is even slightly more active in closed shell activation of these different bonds, and there are two main reasons for such good performance. The first one is the incomplete valence d shell, which drives us to a stronger and more stabilizing orbital interaction with the occupied sigma CH orbital of the substrate. And going to a lower barrier. And the second reason is that the geometry that it adopts, that it drives to a lower, a smaller, let's say, a strain energy. So this is, I mean, these are the main conclusions of this work. It only misses to show you that all the calculations, part of the calculation, the activation strain model analysis have been performed with the PyFrag code that have also been developed by the same authors, and that you can download if you are interested, and allows this whole analysis for catalytic cycle and all kind of different reactivity analysis. And it just misses to acknowledge the people who have helped in performing this work in collaboration between the University of Barcelona and the Free University of Amsterdam, especially Thiago San, who is now postdoc in my group in Barcelona, and professors Trevor Hamling, Matthias Winkelhoff, and Celia Fonseca Guerra from the University of Amsterdam. And finally, I have to thank you all the grants and the money that support my research, and all of you for your attention. In case you have any questions, I will be really glad to answer you. Thank you very much.
Thank you, Dr. Jordi, for your presentation. Is anyone having any questions? Okay, no questions from anyone. Thank you once again for your presence and presentation.
A pleasure. Thank you to all of you.
Okay, so now we can take a lunch break, and we'll be back at 14:15. That is after half an hour. Please stay connected with us. Thank you one and all. Hello, welcome everyone. So we will continue with our sessions after the lunch. So our next presenter is Dr. Joanna Drestezan from University of Gdańsk, Poland. Hello, Dr. Joanna, are you ready with your presentation?
Hello, yes, I'm ready.
Okay, I'm going to make you the presenter. Yes. Please share your screen with us. Yes, it's visible. You can start your presentation.
Wait a second. Okay. Thank you for your kind invitation. I'm Joanna Drestezan. I represent Faculty of Chemistry, University of Gdańsk in Poland. And I'm giving a presentation today on influence of heterocyclic ligands on catalytic properties of oxovanadium 4 complex compounds in olefin oligomerization. The most commonly used polyolefins in the industry are polyethylene, polypropylene, and polybutylene. Polyethylene is mainly used for the production of all kinds of packaging and films. The properties of polyethylene can be divided into mechanical, chemical, optical, or electrical and thermal properties. Polyethylene consists of nonpolar saturated high molecular weight hydrocarbons. Therefore, its chemical behavior is similar to paraffin. The individual macromolecules are non-covalently linked. Because of their symmetric molecular structure, they tend to crystallize. Overall, polyethylene is partially crystalline. Higher crystallinity increases density and mechanical and chemical stability. Most LDPE, MDPE, and HDPE grades have excellent chemical resistance, meaning that they are not attacked by strong acids or strong bases and are resistant to gentle oxidants and reducting agents. Crystalline samples do not dissolve at room temperature. Polyethylene, other than cross-linked polyethylene, usually can be dissolved at elevated temperatures in aromatic hydrocarbons such as toluene or xylene, or in chlorinated solvents such as 3-fluoroethanol. What about polypropylene? Polypropylene is used for the production of, among others, tanks, medical equipment, syringes, or electrical equipment, bathroom fittings, or, for example, children's play accessories. On the other hand, all elements of heating and water installations are made of polybutylene because it almost prevents the migration of water molecules. What are the ways of polyolefins production? The production of polyolefin is related to various methods of synthesis. Among the known methods, the following can be mentioned: cationic or anionic polymerization. In this case, both these reactions have the same reaction mechanism, but the reaction initiator is different. Anionic polymerization reactions are initiated by an active anionic species, whereas the cationic polymerization reactions are initiated by an active cationic species. This is the key difference between anionic and cationic polymerization. Both these polymerization reactions are sensitive to the solvent used. Disadvantage of cationic or anionic polymerization is little control and very low temperatures required. The second one, ring opening metathesis polymerization. In this case, in this kind of polymerization, this is type of olefin metathesis chain growth polymerization. The driving force of the reaction is relief of ring strain in cyclic olefins, for example, norbornene or cyclopentene. A variety of heterogeneous and homogeneous catalysts have been developed. The second one, free radical polymerization. In this case of polymerization, the initiator is a radical and the propagating site of reactivity is a carbon radical. Since this can be initiated by traces of oxygen or other minor impurities, pure samples of these compounds are often stabilized by small amounts of radical inhibitors to avoid unwanted reaction. And when radical polymerization is desired, it must be started by using a radical initiator, for example, peroxide or certain azo compounds. What about disadvantages of this kind of polymerization? Free radical polymerization is difficult to control and high temperatures and pressures are required. And now Ziegler-Natta type, coordination polymerization. This type of polymerization is invented by two Italian scientists, Carl Ziegler and Giulio Natta. They shared the Nobel Prize in Chemistry in 1963 using Ziegler-Natta catalysts to polymerize non-polar monomers. For example, 1-alkene, cycloalkenes, dienes, and alkenes through coordination mechanism instead of common chain or step polymerization. Ziegler-Natta catalysts can be prepared by reacting transition metal halides from groups from 4 to 8, such as titanium tetrachloride, with organometallic compounds from groups from 1 to 3 of the periodic table, such as 3-ethyloaluminum. The titanium catalysts have been widely studied, but other metals like vanadium or zinc have also been proved to be very effective. What about commercial using of Ziegler-Natta catalysts? These catalysts are usually supported, that is, that a bond to a solid with a high surface area. In the case of titanium tetrachloride or titanium trichloride, as the active catalyst, the support is usually magnesium chloride. These catalysts are incorporated into the so-called carrier, which is a material that determines the size and the shape of catalyst particles. One common carrier are spheres of microporous amorphous silica. Titanium compounds on magnesium chloride are packed into the pores and are activated with organoaluminium compounds. One of generations of Ziegler-Natta catalysts are metallocene catalysts. Metallocene complexes are one of the generation of Ziegler-Natta catalysts, despite the high catalytic activity of metallocene complex compounds. Metallocene complexes show unsatisfactory performance in production on industrial scale. Why? Because they are unstable at high temperatures during the polymerization processes carried out. Additionally, some of the metallocene complexes undergo slow decomposition after activation by, for example, metalloaluminoxane. And since the 1990s, research has been conducted on post-metallocene catalysts. The first post-metallocene catalysts were nickel-2 and palladium-2 complex compounds with diimine ligands, which catalyzed the polyethylene formation reaction and the development of polymer chemistry strongly increased in the past few years. And now The field of alpha-olefin polymerization catalysis has developed very much. The discovery of a highly active family of catalysts based on, for example, iron, a metal that had no previous track record in this field, has highlighted the possibilities for further new catalyst discoveries. Britovsek and colleagues introduced the catalyst classification criteria. It means rating of the effectiveness of a catalyst based on its activity, presented in the table. There it can be seen that complexes which have, for example, a catalytic activity of more than 1000 are considered very active catalysts. Our research group previously conducted research on complex compounds of oxo-vanadium-4 complexes with polycarboxylate, for example, oxydiacetate and aminodiacetate ligands, and also with heterocyclic ligands, namely 1,10-phenanthroline or 2,2' bipyridine. We want to check the influence of the type of the central metal ion in the ligand on the catalytic activity in olefin oligomerization. In the case of oxydiacetate, this atom was the oxygen atom, while in the case of aminodiacetate, it was the nitrogen atom. The research concerned the use of oxo-vanadium-4 complex compounds in the oligomerization of 2-chloro-2-propan-1-ol under mild conditions. It means room temperature and atmospheric pressure. The results of the research showed that the tested compounds of oxo-vanadium-4 complexes exhibit high catalytic activities in the studied processes. And for this reason, we undertook further research into oxo-vanadium-4 complex compounds in the oligomerization process. The purpose of this work was to examine the influence of heterocyclic ligands on catalytic properties of oxo-vanadium-4 complex compounds in olefin oligomerization. The dipicolinate oxo-vanadium-4 complex with 1,10-phenanthroline and bipyridine have been tested towards their prediction of catalytic activities in oligomerization reactions of 2-chloro-2-propan-1-ol and 3-buten-2-ol. The series of oxo-vanadium-4 complexes has been synthesized and characterized by potentiometric method, NMA, IR, MLDTOF-MS. The synthesis of complex compounds was carried out in such a way that the substrates were mixed vanadilyl acetyloacetonide, dipicolinic acid and phenanthrolide or bipyridine respectively, and the synthesis was carried out in aqueous solutions which were heated to reflux for about 30 minutes after cooling the complexes precipitate. And then these complexes have been tested by several spectroscopic methods. Analysis of IR spectra confirmed the structures of the complexes. Moreover, elemental analysis also confirmed the composition of the complexes. What about NMA? Good quality NMA spectra were obtained only for the compound complex with bipyridine, most likely because of the water content in the complex structure obscuring the peaks. These complexes have been investigated as precatalysts after their activation by modified metalloaluminoxane. The oligomerization process has been conducted at nitrogen atmosphere, atmospheric pressure, and 2 temperatures, room temperature and 65 Celsius degrees. The oligomerization products have been studied by several methods: NMA, MLDTOF, MS, TG, and IR. Medium intensity stretch band of the hydroxyl group in the oligomer chain participating in hydrogen bonding occurs. At 51 for dipicolinate complex of oxovanadiol 4 complexes, and the same peak is observed for the complex with phenanthroline and bipyridine. Methylene group bending vibration in the oligomer chain is confirmed by peaks in the range from 1320 to 1630 for the first complex, and the complex with phenanthroline. This bending vibration is observed in the range from 1320 to 1633. Carbonyl group stretching vibrations occurs at 1018 for the first complex, and for the complex with phenanthroline, this stretching vibrations is observed at 1016. Moreover, for the complex with bipyridine, this value of the peak is the same. Bond between carbon and chlorine bending vibration in the oligomer chain have been confirmed by the presence of the peak at 590 for the dipicolinate complex of oxovanadium 4 and the complex with phenanthroline. But for the complex with bipyridine, this bending vibration is confirmed by the peak observed at 594. What about MLDTOF MS analysis? This analysis showed that the oligomer sample contains from 6 to 9 mers in the chain for the first complex, from 7 to 17 mers in the chain in the case of the complex of oxovanadium 4 with phenanthroline used as precatalyst, and from 7 to 13 mers in the chain for the last one complex with bipyridine. In the case of the oligomerization of 3-butene-2-ol, the resulting oligomer chains contain from 9 to 19 mers, irrespective of the complex compound used. The most catalytically active is the complex with bipyridine. However, no clear trend was observed in the amount of heterocyclic ligands used in the study. The highest catalytic activity is observed for the complex with bipyridine for both oligomerization processes, for 2-chloro-2-propan-1-ol oligomerization and 3-butene-2-ol oligomerization. In order to illustrate the catalytic activity of similar complex compounds in olefin oligomerization, I have compiled the values of the catalytic complexes activity in the table. As can be seen, the complex compound with oxalate anions show the highest value of catalytic activity in the oligomerization of 2-chloro-2-propan-1-ol. And it is also worth noting that the more metal cation of the complex molecule contains, the better the catalytic properties. It can be seen in this example because the complex of chromium-3 with dipicolinate anions and bipyridine has the catalytic activity equal 26.9, and it is also very high catalysts. In the case of the ethylene oligomerization carried out under mild conditions, The highest catalytic activity was demonstrated by the dipicolinate complex compound of chromium-3 with 4,4' dimethoxy 2,2' bipyridine. In order to summarize the presentation, I illustrated the changes in the catalytic activity of the analyzed oxovanadium-4 complexes, of which the strongest catalyst turned out to be a complex with bipyridine. But it is worth noting that the world literature reports that when designing new catalysts, one should be taken into account ring deformation in heterocyclic ligands, which should improve catalytic activity. Okay, that's all. Thank you for your attention.
Thank you, Dr. Zuana, for your presentation. Is anyone having any questions? Okay, no questions from anyone. Thank you once again for your presence and presentation.
Thank you very much.
Okay, so our next presenter is Dr. Chai Sia Lee from University of Nottingham, United Kingdom. Hello, Dr. Chai Sia. Are you ready with your presentation? I'm sorry, you are muted. Kindly unmute yourself. We cannot able to hear you.
Okay, can you hear me now?
Yes, yes. You can
Okay.
share your screen with us. I have given you the permission. Yes, it's visible. You can start your presentation. Now? Yes.
Okay. Okay. Good afternoon, everyone. I'm Jesslyn, a postdoc researcher from the Green Chemical Beacons from the University of Nottingham, UK. Thank you for giving me an opportunity to present on this webinar. Today, I'm going to talk about supercritical water gasifications, SCWG, with dinocellulosic biomass waste as a feedstock, focusing on the economic analysis of non-catalytic SCWG at 600 degrees Celsius versus catalytic SCWG at 400 degrees Celsius. Okay. Basically, SCWG is a combined thermal decomposition and hydrolysis process for converting wet biomass feedstock with high water content with more than 80 weight% to syngas that contains hydrogen, methane, CO2, and CO by using supercritical water as a reaction medium. In this process, the target gas product is hydrogen. SCWG has some advantages when compared to conventional gasification process. First, it bypasses the need for an energy-intensive drying step. Second, it has shorter residence times within seconds to minutes. Okay, up to now, SCWG process are mainly conducted in lab scale. There are a few pilot plants that has been built. These diagrams show one example of the pilot plants built in Germany by using corn silage with ethanol as a feedstock. The feed contains 20 kg per hour biomass and 80 kg per hour water, and it operates at 600 degrees Celsius and 350 bar. Okay, And this slide shows the supercritical condition of water. Water reaches critical points when it reaches 221 bar and 374 degrees Celsius. At supercritical conditions, it's impossible to distinguish between liquid and gas phase, and therefore chemical reactions are conducted in a single phase only. And due to that, the mass transfer limitation between phases is eliminated, and it leads to shorter residence time. Supercritical water has the density of liquid water and the viscosity of water vapor, which enhance the mass transfer and solvation properties. And in addition, it has a chain structure with separated polar water molecules corresponding to a decrease of the dielectric constant, which increases the solubility of organic polar substances in it. Supercritical water is an environmental friendly, homogeneous, and non-polar solvent with a strong ability to break down organic compounds, which can result in the production of syngas. The solvation power of supercritical water and its ability to break down biomass components and use hydrogens are adjustable by tuning the process condition and the use of catalyst. Supercritical water gasification process basically occurs through a few main reactions. Okay, the first one is steam deforming reactions, whereby the biomass components react with water vapor to form CO2 or CO and hydrogens. The second type is water gasification reactions, whereby the CO reacts with water vapor to form CO2 and hydrogen. And the last one is methanation reactions, whereby the CO or CO2 reacts with hydrogen to form methane and water. In this process, steam deforming and water gasification reactions are desirable because these two reactions are responsible for the production of our target gas, which is hydrogens. Okay, normally wet biomass with water content of more than 80 weight percent and high organic contents is selected as the feedstock for this process. And the feedstock can be categorized into 4 different types. The first one is model compounds such as cellulose, hemicellulose, and lignins. Many studies have been conducted using model compounds in order to get a fundamental understanding of SCWG. Second type is very wet, real biomass waste such as wheat straw, corn cob, sugarcane bagasse, and almond cell. Some studies have been reported by using biomass waste as a feedstock. However, real biomass has complicated components that may affect the syngas productions. The third type is wastewater streams such as olive meal, wastewater, sewage, sludge, and there are just a few studies on this feedstock. The last one is algae, and there are limited studies by using algae as a feedstock. Okay, this slide shows the main variables that affect the gasification efficiency. The first variable is operating temperature. Normally, the study temperature is between 400 to 600 degrees Celsius. With increasing of temperature, there's an increase of hydrogen and CO2 use, coupled with a decline in CO and methane use. This indicates that the solvation of biomass components in supercritical water and water gasifications are promoted at elevated temperature. The second variable is reaction time. For batch mode process, the reaction time is between minutes to tens of minutes. For continuous mode process, the reaction time is about tens of seconds. Increases of reaction times normally leads to the rising of hydrogen and CO2 and methane use, but decreasing of CO use. This indicates that water gasification and methanation reaction are favored at longer reaction time. Another variable is the biomass feedstock concentrations. Normally, the study feedstock concentration is between 5 to 25 weight percent. A decrease in feedstock concentration means that more water content for the steam reforming and water gases ratios, which increase the hydrogen and CO2 use and decrease the CO and methane use. Okay, this slide make a comparison between non-catalyzed and catalyzed SCWG. For non-catalyzed gasifications, normally there is a higher CO concentration due to intrinsically low rate of water gasifications, and it requires a very high temperature, which is more than 600 degrees Celsius, in order to achieve complete conversions. In contrast, for the catalyzed gasifications, the reaction temperature can be reduced, such as from 600 to 400 degrees Celsius, by using catalysts to reduce the activation energy. And due to lower operating temperature, the equipment and operating costs are reduced. In addition, catalysts can facilitate the seasoning of CC and CS bonds and favor the water gasifications, which improve the hydrogen yield and reduce the chalk formation. And up to now, there are two types of catalysts that have been used, which are homogeneous and heterogeneous catalysts. Okay, for homogeneous catalysts, it's basically alkali catalysts, such as calcium hydroxides. Most investigation of homogeneous catalysts were performed in batch mode at temperatures below 600 degrees Celsius, and the results show that the hydrogen used at 400 to 500 degrees Celsius was increased by using homogeneous catalysts. However, this kind of catalyst has some drawbacks. First, the catalyst recovery is difficult to achieve. Second, there's an additional cost for the ongoing addition of fresh catalysts. And third, the generated liquid waste containing alkali catalyst is difficult to treat. And due to the drawbacks of those homogeneous catalysts, so there are more research on heterogeneous catalysts. The first type is metal-based with support materials. The type of metals includes nickels, deuteriums, cobalt, copper, and ions. Nickel and deuterium have higher efficiency because it has higher ability to catalyze CC bonds, breaking and promote water gasification, which increase the hydrogen yield. Deuterium is shown to be more active than nickels due to higher metal dispersion and BT surface area on the support materials. However, deuterium is far more expensive than nickels. Therefore, nickel is commonly selected, followed by deuterium with smaller percentage ruling. Up to now, some metal-based catalysts have shown comparable catalytic effect as alkali catalysts. Okay, there are three types of support materials that can be attached on the metal surface. The first type is activated carbons. It has high surface areas. However, the drawback is it will deactivate after a few hours of operations. The examples are nickel with activated carbons and deuterium with activated carbon. Okay, the second type is carbon nanotubes that has high surface area, thermal stability, and high mechanical strength. One example is nickel with carbon nanotubes. Okay, the last type is metal oxides. These types can significantly enhance the hydrogen yield at lower operating temperatures such as 400 degrees Celsius, but only for single use. The stability and additivity drop for repetitive use is drawback. The examples include aluminum oxides, titanium oxide, and magnesium oxide. Okay, natural mineral is another type of heterogeneous catalyst. For example, trona, borax, dolomite, and olivine. The advantages include low cost, readily available, and no need to recover. However, the drawback is its catalytic effect is less significant than alkali catalysts and metal baths with support materials, and therefore there are limited study on this type of catalyst. Okay, now I'm going to talk about the economic study for catalytic and non-catalytic SCWG process. And this study was conducted by using Aspen Plus simulation software. The purpose of this study is to compare the capital and operating expenditures between continuous mode catalytic SCWG at 400 degrees Celsius and non-catalytic SCWG at 600 degrees Celsius. In this modeling process, wheat straw was chosen as a feedstock because it's largely generated in UK every year. The biomass was defined as a non-conventional solid and modeled by using its proximate and ultimate analysis. The proximate analysis includes moisture contents, ash contents, volatile metals, and fixed carbon. The ultimate analysis includes carbon, hydrogen, oxygen, nitrogen, and sulfurs. Okay, this figure shows the diagram of the SCWG process. Okay. In this process, the water was pumped to 221 bar by using a high pressure pump, and then it was heated to supercritical temperatures through a heat exchangers and a heater before it was fed into the reactor. On the other hand, the biomass was pumped to 221 bar to another high pressure pumps, but and then it was fed into the reactor at room temperature without any heating. So when the biomass was mixed with supercritical water in the reactor, the biomass was rapidly heated. Okay, and in these models, a RU block with Fortran subroutine was used to convert the biomass into carbon, oxygen, hydrogen, nitrogen, sulfur, and ash. And then our GIPS reactor was used to predict the equilibrium product compositions by applying direct minimization of GIPS-free energy. Okay, and pair remission with Boston's Matthews missing rules was selected as a property method to calculate the product used from the reactors. The products include hydrogen, methane, CO2, CO, water, and ash. Okay, after reactions, the product streams was cooled down through a heat exchangers and then depressurized to ambient condition through a pressure regulator. And finally, the gas and liquid products were separated in a gas liquid separator. Okay, the operating conditions for this process were 400 or 600 degrees Celsius, 400 for catalytic process and 600 for non-catalytic process. And the operating pressure was 221 bar, and the feedstock concentrations was 5 weight%. The feed streams was 20,000 kilogram per hour that contains 5 weight% with straw. And there was a constant feeding of metal salts. The metal salts were nickel nitrate hexahydrate and magnesium nitrate hexahydrate. Okay, the metal salt was fed together with the biomass stream into the reactor for the in situ formation of 10 weight% nickel with magnesium oxide catalyst. Okay, this slide shows the value for different parameters in these models. The operating plant life was estimated to be 20 years, and the operating hours were 8,760 hours. And then the cost for the water, electricity, natural gas, with straw, and the nickel and magnesium metal salts for catalytic formations were estimated based on reliable online informations. And this slide shows the result of this economic study. When compared to catalytic SCWG, Non-catalytic SWGs require significantly higher heating costs because of higher operating temperatures at 600 degrees Celsius, and this contributes to higher utility costs. In addition, non-catalytic SWG requires the selection of high-grade heat-resistant and anti-corrosive tubing and fittings materials, such as in corner 625, which is more costly. On the other hand, catalytic process at 400 degrees Celsius can use stainless steel 316 as the tubing material, and this material is less costly. And due to all this, all this lead to higher capitals and operating costs for non-catalytic SCWG process at 600 degrees Celsius. Okay, in conclusions, SCWG is a promising and potentially eco-friendly technology that rapidly decomposes biomass to produce syngas that contains hydrogen, methane, CO2, and CO. And the use of dinocellulosic biomass as a feedstock has some advantages, such as abundant availability, low-cost nature, environmental friendly features, and high hydrogen use at supercritical conditions. And then elevated reaction temperatures, longer residence times, and low feedstock concentrations favor water gas reaction that promote hydrogen productions. And that's the development of heterogenic catalysts, particularly metal-based with support materials, have received more attention due to its ability to lower reaction temperature from 600 to 400 degrees Celsius, whilst increasing gasification efficiency. And then the economic studies show that catalytic SCWG at 400 degrees Celsius is theoretically more economically viable than non-catalytic SCWG at 600 degrees Celsius. And now my current work focuses on the explorations of low or zero or negative value biomass solid waste and biomass wastewater. That's largely available all year round in the UK. They can produce high hydrogen yield through catalytic SCWG process. In addition, I also focus on the development of catalysts that can be formed in situ, which enable low temperature SCWG process with gasification efficiency comparable to high temperature SCWG process. This can prevent performance drop during continuous run and make the process economically feasible for scaling up. Before I end my presentation, I would like to express my special acknowledgement to Green Chemical Beacons at the University of Nottingham and also my supervisors, Professor Alastair and Professor Alex Conrary. This is the end of my presentation. Thanks for your kind attention, and I'm happy to take any questions.
Thank you, Dr. Chai Sia Lee, for your presentation. Is anyone having any questions? Okay, I think there are no questions from anyone. Thank you once again for your presence and presentation.
Thank you.
Yeah, moving on to our next presentation. It's from Dr. Cesar Jurovic from Institute of General and Physical Chemistry, Serbia. Hello, Dr. Cesar. Are you ready with your presentation? Hello. We cannot able to hear you. Can you able to hear me? I'm sorry, your voice is not audible to us. Okay, I think he is having some network issue. We will wait for a few more minutes. Hello, Dr. Cesar. Your screen is visible to us, but we cannot able to hear you.
Can you hear me now?
Yes. Now it's perfect. Please start your
Okay, I
presentation.
had some problem with microphone, sorry.
Okay, it's happened sometimes. You can start your presentation.
Okay, thanks. Hello, my name is Sasha Djurovic. Firstly, thank you for your invitation to present here. I will talk about rosemary essential oils as a promising source of bioactive compounds, chemical profile, biological activity, thermal properties, and possibility of utilization as antioxidant agent. Okay. Wait, please. Oh. Okay. We know that rosemary is a worldwide cultivated plant for essential oil. As a spice, it is also used as a source of bioactive compounds. Essential oils, so these plants show different biological properties such as antioxidant, antimicrobial, and etc. It's really widely investigated. Chemical profile of the essential oils differs depending on the different factors such as geniality, seasonality, environmental conditions, agronomic condition, and varieties in plant itself. Camphor, alpha-pinene, and eucalypto are mostly marked as the principal compounds in the rosemary essential oils. However, borneol, bornyl acetate, and verbenone were also reported as the principal compound in some varieties of rosemary. So these varieties can influence, of course, the behavior, thermal property, and biological activity, and of course, quality of the oil itself. So there is a generally need to analyze the oils prior to any usage. Sunflower oil is one of the most important and common edible oil all around the world. It is widely used for the food preparation, but it is susceptible to the oxidation processes. Sensitivity of this oil is due to the presence of the unsaturated fatty acids, especially linoleic and linolenic acids. Oxidation of the fatty acids causes rancid odor, unpleasant flavor, discoloration, and etc. Several factors influences the occurrence of the oxidation. Exposure to the oxygen, light, high temperature, presence of the metal ions, especially iron and copper. To prevent the oxidation, synthetic and natural antioxidants are added to the sunflower oil. However, natural antioxidants are more favorable due to lack of the side effects in comparison with synthetic ones. So experimental part of this work was commercially available essential oils from Russia and Serbia were analyzed using GCMS. Presence of the metal ions was assessed using ICP OES methods. Thermal properties were analyzed using differential scanning calorimetry. Antimicrobial activity was also assessed against 4 bacteria, 1 yeast, and 1 fungi strain. And after all, both essential oils were added to the sunflower oil to investigate their antioxidant capabilities during the frying process, which is simulated by DSC. Chemical composition, we can see our chromatograms. Serbian oil was a bottom chromatogram and rosemary Russian oil was upper. We can see that both samples are very similar. So when you present results like this, same compounds dominates in the both samples. So alpha pinene 23% in Serbian oil and 70.76% in Russian oil. Eucalyptol 70.79% in Serbian and 23.40% in Russian sample. Sorry, camphor 40.39 in Serbian and 70.17 in Russian oil, respectively. When we compare the quantitative results, we could notice that all dominant compound showed quite higher content in the Serbian sample than in Russian sample, which is quite interesting. Elemental profile. Okay, we expected a lot of macro bulk or bulk elements such as potassium, natrium, magnesium, and calcium. There is a lot of iron in a Serbian sample. There is also chromium in a Serbian sample. Phosphorus was also in a high amount in both samples, and sulfur. Polluting elements are presented in very low amounts. Of course, arsen is not found, which is very, very good. Antimicrobial activity. When we compare Serbian and Russian oil, Serbian oil showed lower activity against all analyzed strains. By this diffusion method, Russian oil is more potent than standard compounds used for comparison. It's very, very high antimicrobial activity, which is also very interesting because we expected vice versa because of the chemical composition. However, presence of the other minor compounds actually may influence such results. Also, minimal inhibitory concentration of Russian sample is quite lower than Serbian in case of Serbian samples. Where for yeast and fungi, Serbian sample need more than 50% of the solution to inhibit. Thermal properties. Because of similarity, we can see here that because of a very similar profile in both samples, same compounds are major compounds. The thermal behavior is very similar, which could be seen on all three thermograms. Activation energy of evaporation are also very similar because of the same reason. In both oils, 4 compounds dominates in high percent. Antioxidant activity is analyzed by DSC. This is percentage of added oil by weight in sunflower oil. We can see that oxidation starts after 18 minutes of, in the case of the clean sunflower oil. In the beginning, Russian sample influence positively, slightly positively on the oxidation process. Actually, delayed start of oxidation. Oxidation starts after 20.3 and 20.2 minutes, while Serbian oil in low concentration also slightly move the oxidation process, delayed. However, when we added Russian oil in 1, 5, and 10%, results were opposite. Russian oil actually increased the oxidation and lowered the oxidation time comparing to the clean sunflower oil. So when we added 10% of Russian oil, oxidation start after 4.6 minutes. However, 1% of Serbian oil significantly increased the oxidation time, and protect the sunflower oil. Negative influence was also obtained at 5% and 10% of Serbian oil. So in the conclusions, we can conclude that geographical origin significantly impacts on the chemical profile of the investigated essential oil. Also, Russian oil shows slightly higher antimicrobial activity comparing to the Serbian oil, but Serbian oil proved to be more potent antioxidant agent after injected to the sunflower oil. So generally, application of the essential oil will highly depend on the chemical profile. So chemical profile must be established first. And thank you for your attention. And thank you for invitation here.
Thank you, Dr. Sesha, for your presentation. Is anyone having any questions? Okay, no questions from anyone. Thank you once again for your presence and presentation.
Thank you.
Okay, moving on to our next presentation. It's from Dr. Fecchetti Giorgio from University of Milan, Italy. Hello, Dr. Giorgio. Are you ready with your presentation?
Yeah, good morning, everybody. Can you hear me?
Yes. Yes, you are the presenter now. Please share your screen with us.
Yeah. I think, okay.
Yes, perfect.
Perfect. Okay, just a moment that I share presentation. Okay. Can you see the presentation?
Yes, yes. You can start your
Okay,
presentation.
perfect. Just a moment that I can't. Okay. Okay, so thank you first of all for giving me this the opportunity to present and to attend this webinar. Instead, the work I'm going to present is entitled Artificial Metal Enzymes based on vancomycin for stereoselective catalysis in aqueous media. Transition metal catalysts and enzymes possess unique and often complementary properties. So in the last decades, researchers tried to combine the structure and reactivity of metals and peptides in the so-called artificial metal enzymes. Artificial metal enzymes are hybrid catalysts in which a transition metal complex is embedded in a biological environment, and these hybrid systems combine the broad scope of organic transformation catalyzed by metal catalysts with the exquisite selectivity of enzymes. As described by Whiteside and Wilson in 1978, a metal enzyme could be defined as it follows: a globular protein modified by the introduction of a catalytically active metal at an appropriate site that could in principle provide an exceptionally well-defined steric environment around that metal, and should do so for considerably smaller effort than would be required to construct a synthetic substance of comparable stereochemical complexity. So this means that in artificial metal enzymes, incorporating an organometallic compound in a three-dimensionally defined biological structure can in principle create a transition metal catalyst with the features of an enzymes. And in order to achieve this goal, covalent, dative, or supramolecular anchoring strategies for the metal moiety, the so-called first coordination sphere into the biological entity, have been pursued. The supramolecular anchoring, in particular, could exploit, among the others, the so-called Trojan strategy, here depicted, based on the covalent attachment of the organometallic moiety to a substrate that show high affinity for the protein, such as the one explored in the well-known biotin streptavidin technology. On the basis of the pioneering work by Professor Bard, in my research group, it has been recently developed an artificial imine reductase in which a chiral 1,3 diamine ligand in coordination with an iridium center was anchored to streptavidin and employed in the stereoselective reduction of the salsolidin precursor. The use of this poorly understood type of diamine ligand shed light on those protein residues that most strongly affected the selectivity of this reaction. And in this study, as you can see, a genetic optimization of the host protein was explored, and this aspect was carried out under the guidance of computational studies that helped us to highlight the protein residues that more deeply affect the stereoselectivity of this reaction. And in fact, in the presence of the streptavidin mutant S112C, the reaction proceeded affording the product in an encouraging 65% EE. Moving forward on this field and with the aim to expand the library of artificial cofactors, we applied a chemical optimization strategies to the synthesis of different biotinylated catalyst precursor, which was then reacted in situ with a series of different binding ligands to prepare a new class of artificial metalloenzymes. We focused on diamine chelating ligands with different steric and electronic features. Two achiral diamines based on imidazole and the chiral 1,3-diamine that has been applied in the previous study as a probe to guide the genetic optimization of the host protein, and the 8-amino tetrahydroquinoline here called CAMPI, that has been recently identified by our research group as an efficient chiral ligand in iridium complexes for the asymmetric transfer hydrogenation of different substrates. We reasoned that this goal would be more easily achieved by tethering the biotin anchor directly to the cyclopentadienyl moiety, so that the reactivity of the first coordination sphere would be exclusively dictated by the features of the chelating amines around the iridium center. In the case of 1,2-diamine CAMPI ligand, a better enantioselectivity was obtained in all cases. And considering the ability of CAMPI to induce chirality in the corresponding iridium complexes and to affect the catalytic activities depending on the selected streptavidin mutant, both enantiomer, the R and S enantiomer of CAMPI, were evaluated. Considering that the best enantioselectivity were obtained in both cases with the streptavidin, the presence of the streptavidin mutant S112M, the effects of buffer at different pHs and the streptavidin mutant ligand ratio on the reactivity and selectivity of the system were evaluated. The mutant, the streptavidin mutant and the ligand ratio variation was based on the tetrameric structure of streptavidin, which exists as a dimer of dimers, which one providing a biotin binding site. The streptavidin mutant metal cofactor ratio affected substantially the enantiomeric sex, and in fact, for a ratio of 1 to 2.5, the enantioselectivity highly increased, reaching a great 83% EE. These changes in enantioselectivity in the imine reductase activity was consistent with the rigid structure of CAMPI and with the metal cofactor probably fully occupying only one active site in the streptavidin mutant. And this observation indicates that the steric hindrance played an important role in stabilizing a specific second coordination sphere environment, and thus influencing which prochiral phase of the substrate can approach the hydrid to afford the preferred product enantiomer. Under these conditions, when two RR metal cofactors simultaneously occupied two close-lying biotin binding sites, one in a dimer and the other in the opposite dimer of the tetrameric streptavidin, each monomer is active and might behave independently with no interaction between the adjacent cofactors, thus increasing the enantiomeric sex to the experimental obtained 83% EE. In the last decades, the widespread presence of metal ions in biological systems and the possibility of using well-known natural structures as ligands in metal complexes have inspired different research groups to exploit biodiversity and to investigate new artificial systems. DALBA peptides such as vancomycin but also teicoplanin or ristocetin could be employed as an innovative second coordination sphere alternative to the classical biotin streptavidin system. And to the best of my knowledge, this is the first time that such an anchoring system has been explored for the synthesis of artificial metal enzymes. This glycopeptide family is made up of heptapeptides oxidatively linked through aromatic amino acids and variously functionalized with chlorine atoms and glycosidic or lipidic chains. Their potential as a source of chirality stems from the presence not only of the aminoacidic chains chiral by definition, but also from their tropoisomeric structure induced by the restricted rotation around the aryl bonds. DALBA peptides are known for their strong antibacterial activity due to the interaction with the dimer d-alanine in the terminal chain of bacterial cell wall peptidoglycan that is marked by a dissociation constant of 10 at minus 17 molar. So even this is an interaction even tighter if compared to the biotin system. Vancomycin selectively binds this dimer d-alanine, and the complex was found to be stabilized by an intensive array of hydrophobic contacts and by 5 key hydrogen bonds. Starting from these premises, we decided to synthesize a new class of ligands, starting from the common ethylenediamine monoboc moiety that has been reacted with a different functionalized chlorosulfonyl benzoic acid, here used as a spacer, carrying the carboxylic function necessary for the coupling with the dimer d-alanine in ortho, meta, or para position on the aromatic ring. And this variation has been done with the idea to influence the conformational structure of the spacer and to modify the distance between the catalytic metal complex and the second coordination sphere induced by vancomycin. The synthesis, as you can see, proceeded as reported in the schema here depicted for both the meta and para ligands, substituted ligands. Unfortunately, the synthesis of the ortho functionalized ligand wasn't obtained either by solid phase synthesis or by liquid phase synthesis. In fact, both these synthetic approaches resulted in this cyclic thiocarbamate byproduct. After the coupling step with the dimer d-alanine dimer, the diamine ligands that were obtained was employed for the synthesis of the iridium metal complexes, precatalysts, and employed for the preparation of the corresponding artificial metal enzymes in the presence of vancomycin. Based on computational studies revealing the promising behavior of the meta ligand in respect to the para-functionalized one, we decided to focus our efforts on the optimization of the meta hybrid catalyst. In order to confirm the supramolecular interaction of the iridium precatalysis with vancomycin, both circular dichroism and two-dimensional dose experiments, NMR experiments, were carried out. Looking at the circular dichroism spectrum, a metal to ligand charge transfer band at around 348 nanometer can be clearly detected due to the presence of the iridium when the supramolecular interaction takes place, and moreover the marked decrease in intensity of the vancomycin band at the 285 nanometer led us to conclude that the vancomycin aromatic rings are somehow involved in the coordination. From the NMR dose experiments, we can see that vancomycin clearly form aggregates in water when it's present alone, but the increase in the hydrodynamic radius of the iridium precatalyst in the presence of one equivalent or two equivalent of vancomycin unequivocally established the formation of the vancomycin-based hybrid system. After confirming the supramolecular formation of the artificial metal enzymes on the basis of the scaffold cofactor interaction, we decided to evaluate the potential of this hybrid system as an artificial imine reductase in the asymmetric transfer hydrogenation of cyclic imines. Why cyclic imines? Because the corresponding reduction products in an anti-pure form are key functionalities in many biological active molecules. And for this reason, extensive efforts have been made with the aim to develop an efficient and practical method for their preparation. And in this regard, asymmetric transfer hydrogenation provide a valuable process with the iridium-3 catalyzed asymmetric transfer hydrogenation that has been recently widely investigated within this context due to the possibility to the use of environmentally friendly reaction conditions, such as the use of aqueous media. Despite the achievements made in this field, the asymmetric reduction of cyclic imines, such as dihydroquinolines or isoquinolines and quinolines, important pharmaceutical intermediates for the production of complex alkaloids or beta natural amino acids, is still an unmet goal, thus providing the need for further investigations. The synthesized iridium-based hybrid system in the presence of one or two equivalent of vancomycin was prepared in situ after 1 hour complexation time, and its catalytic activity was evaluated in the asymmetric transfer hydrogenation of the here reported cyclic imines A, B, and C. Different reaction conditions were screened: buffer, the type of buffer, the pH, the temperature, the substrate concentration, the substrate catalyst ratio, and the vancomycin iridium precatalyst ratio. The data reported reported in this table were obtained under the optimized reaction conditions. That it means a pre-complexation time of 1 hour, substrate catalyst ratio of 50:1, a final substrate concentration of 16 millimolar, and a vancomycin iridium precatalyst of 2:1 in the presence of sodium formate 3 molar as hydrogen donor. While the para substituted hybrid system resulted active but lacking of stereoselectivity, the meta hybrid system, as expected by computational studies in acetate buffer 0.1 molar at pH 5, resulted at the best medium for substrate A, affording the salsolidine precursor in quantitative yields with a good 48% EE, and whereas in the case of substrate B, the quinaldine B, the product, although the modest conversion, was isolated in a significant 71% EE. Instead, in the case of substrate C, the precursor of chiral sultam, the mass buffer at pH 6 resulted the best medium, affording the product in a modest but unprecedented 34% EE. It's worth noting that this the remarkable 71% EE obtained in the reduction of quinaldine was obtained by increasing the vancomycin catalyst ratio to 4:1, underlying the great impact of the second coordination sphere on the stereoselectivity of the reaction, and as confirmed by the fact that when vancomycin is absent, the reaction proceeded affording the product only in a racemic mixture. And this aspect can be explained considering that vancomycin strongly dimerized in a cooperative manner with a ligand binding. That it means that the ligand binding induces a conformational change that by inducing flexibility in the vancomycin structure allows the formation of a back-to-back network of hydrogen bonds that results in the formation of a microcyclic chiral basket-like structure around the metal center, and that is responsible for the increasing enantioselective performance of the iridium first coordination sphere. In the future, the scope of the this catalytic reaction can be further expanded by the variation of the linker, so the variation introduced in the first coordination sphere that would allow to place the metal precatalyst in a different position within the second coordination sphere, thus changing the reactivity and introducing a unexplored reactivity towards different substrates. Moreover, starting from the assumption that the dimer, the alanine is essential for the anchoring of the metal precatalyst, in the future it will be interesting to evaluate the use of the well-known modified alpha peptides, such as the teicoplanin or ristocetin, as a new second coordination sphere. So just an acknowledgement to my group of researchers here in the University of Milan, and all of you for your kind attention. And of course, thanks to the organizing committee for inviting me to attend this webinar. Thank you.
Thank you, Dr. Giorgio, for your presentation. Is anyone having any questions?
Of course, if someone is interested in more details, he or she can be contact me at my email address.
Okay, no questions from anyone, I think. So thank you once again for your presence and presentation, Dr. Giorgio.
Thank you so much.
Okay, bye. So our next presenter is Dr. Lucia Steenkamp from CSIR, South Africa. Hello, Dr. Lucia. Are you ready with your presentation?
Yes, I am.
Yes, so I'm going to make you the presenter. Just a minute, okay. Yes, you are the presenter now. Please share your screen with us.
Can you see my screen?
Yes, yes.
Okay. Okay, thanks for the opportunity to present to you today. Okay. So my talk today is on a very efficient two-step green process to produce amber furan. And we've done this work at the CSIR. It stands for Council for Scientific and Industrial Research, and we're a research organization in South Africa. Now, there is a few people that's already presented on biocatalysis. Just to maybe give a definition again of biocatalysis. One can use natural catalysts such as your protein enzymes or your microbes, and they can perform then chemical transformations on organic compounds. So you can use both the enzymes still in the microorganism, or you can use it in several states of isolation to then do the biocatalysis for you. Now, there's a huge demand these days for green technologies when people want to commercialize technologies, and biocatalysis is really one of the greenest technologies that you can get, and it adheres to 10 to 12 of the principles of green chemistry. And I think most of the people here today will know about the 12 principles of green chemistry. So consumers these days demand newer and greener, environmentally friendly processes. And especially this is true for when a product has to be ingested or used on your skin, when it's used as flavored and fragrances, as pharmaceuticals, or as cosmetic products. What you can do is to get natural products is to extract it from the natural source, but everybody knows your yields are normally very, very low. And biocatalysis and biotechnology can be used to replace these time-consuming and very low-yielding extractions. Harsh and dangerous chemical steps in the synthesis of intermediates and final products might be replaced by biocatalysis. And I hope I can illustrate this with the product that we've developed. And unfortunately, biocatalysis never stands on its own. You will always need some additional green chemistry steps to come up with a complete process. So where biocatalysis fits into the 12 principles of green chemistry, I think biocatalysis is really one of the ultimate green technologies because it prevents waste. You use very much less hazardous chemicals. You can design safer chemicals. You minimize the use of solvents and other auxiliaries. It's extremely energy efficient because you normally work near ambient temperatures. You do not need these high temperatures to accelerate the reactions, or you also do not normally use very low temperatures to avoid volatile reactions that can run away. We use renewable feedstocks as substrates or growth media. In general, we can reduce the derivatives as well as unwanted byproducts. Use catalytic amounts rather than stoichiometric reagents. Your growth media is very easily degraded. Real-time analysis is possible, and your chemistry is much safer, and therefore you can reduce accidents, especially when you commercialize the technology. But like I said, biocatalysis is seldom used on its own. It's a very useful supplementary technology in the chemical industry, and often your precursors that you require must be made by chemical synthesis, and very often, almost always, your downstream process requires some green chemistry and solvents to get the final product. I think everybody knows that enzymes these days can be used very effectively for stereoselective synthesis of products that's sometimes really difficult to synthesize by classical organic chemistry. And biocatalysis can often replace several chemical steps, and I hope I can illustrate this with this example of the synthesis of amberfuran. And enzymes, initially people only used them in water, but we know that they can now be done in organic solvents where the substrates do not dissolve in water. So this amberfuran that I want to use an example as the power of biocatalysis. Now ambra basically is a metabolic product that comes from the sperm whale. So the whales ingest different foods, and there's also some injuries that take place, and then it forms these big chunks that with time it excretes into the sea. Now you can imagine this poor sperm whale swimming around in the sea, minding its own business, and then because of this highly valuable product, people have started to kill the sperm whales before they actually excrete these chunks of ambra. And for this reason, whales are now protected under the Convention of the International Trade of Endangered Species and Wild Fauna and Flora, because they were actually killed for this ambra. Now what happens as soon as the ambra is excreted into the sea, it floats on the sea surface, and there it is exposed to sunlight and air on the surface of the sea, and with time then it actually forms new products. And this it's a number of oxidation products, and they've actually got very specific odors that is formed in these chunks. And this amberfuran is a very valuable essentializing fixative in perfumes. Now, initially, Firmenich did a complete synthesis of ambrox, and they call of ambrox, and they actually called it ambrox, but this is a registered trademark of Firmenich. And the price of the synthetically produced ambrox is quite high, at $1,000 a kilo. And commercially, at the moment, it's still made from sclareol in 8 chemical steps. But our commercial partner has chosen the name amberfuran instead of ambrox, not infringe on the trademark of Firmenich. And your natural ambrox is even more expensive, and it's very sought after in perfumes and other fragrance applications. So there's the structure of ambrox minus ambrox, and there's a number of the very expensive perfumes that use this fixative to fix the very expensive fragrances. Now this is basically just the root when the amberfuran is formed in this big amber chunk while it's floating on the sea. So the precursor is basically ambrane, and some oxidations take place during this floating on the sea, and you form the amberfuran. Now there's quite a number of other natural starting compounds that you can use to produce amberfuran. I've just chosen 2, and we've actually written a whole review article in 2020 in Molecules on the different routes starting from natural compounds to make amberfuran. There's 2 of them. You can start with a synthesis from carbone. It's not a natural synthesis, it's just a natural starting material, and like you can see there's a number of 9 or 10 steps to get just to the diol, or even some of the other precursors. So you can also start with abitic acid, also going through a number of steps, chemical steps, to get to a diol that can be then converted to the final amberfuran. Now, when you look at the current commercial synthesis to produce this intermediate diol from the sclareol, It's 7 steps. And so you start with sclareol, which is obtained from the claris sage plant, so extracted from there. They do an epoxidation using peracetic acid and ethyl acetate, but it takes 8 days to do this epoxidation. This is followed by pane rearrangement in sodium hydroxide overnight. This is followed by acid cyclization in sulfuric acid at 0 degrees Celsius because of the volatility of this reaction. Then you start to add sodium periodate for again 16 hours in darkness to form the aldehyde, which is then oxidized using a Jones reagent, chromium tetroxide in concentrated sulfuric acid. You form oic acid, which is then treated with again with peracetic acid overnight to get the sclareolide, and this is then treated with lithium aluminium hydride in tetrahydrofuran for 3 hours at room temperature to get the intermediate diol. Now this diol then has to still be converted to the final ambrafuran, and it's often done by oxanic butyl lithium in tetrahydrofuran, and they use also tosyl chloride and pyridine in some cases to do the cyclodehydration. Now, I just want to mention some of the problems associated with this chemical synthesis, and you can imagine on commercial scale, this is aggravated all these problems. So the first reaction takes 8 days, which is quite long. You generate quite a bit of waste, and this has some of it has to be disposed of in a special manner because of the toxicity and the harshness of the chemicals. I can just mention here that they've actually found that for 1 kilogram of product, they produce 207 kilograms of waste. A number of byproducts are formed. They use quite harsh chemicals such as butyl lithium and hexane. I think most chemists will know that butyl lithium is quite dangerous. It's quite water reactive and extremely flammable. It's very corrosive and causes all kinds of health problems like severe burns and also chemical pneumonitis, which can be fatal. And also, if you're chronically exposed to it, you may have kidney damage. Then tosyl chloride, again, in contact with water, it liberates toxic gas. It also causes quite severe burns on all exposure routes, serious effects on your respiratory system. You have to do the reaction at 0 degrees and adding the agents stepwise because it's very, very volatile. The last cyclodehydration reaction, which they do with this tosyl chloride and pyridine. We all know that pyridine is quite toxic and cause liver damage, and it also has a effect on the final fragrance. Now, sometimes they do replace the pyridine with sodium hydride and sodium tertiary amyl alcohol, but sodium hydride on its own is also very dangerous when wet and very caustic. It reacts very violently with water and forms a flammable and explosive gas, hydrogen. So you can imagine if you then do this on large scale, commercial scale, there is severe health risk for the operators. So at the CSIR, we actually came up with a 2-step green process. We still start with sclareol, like the commercial route, but we found a microorganism, Mycosoma roseo-niger, which is a yeast-like fungus, and it basically cuts out 7 of the 8 chemical steps. We feed it sclareol, and within 72 to 96 hours, we get this ambrodiol intermediate. And then we also came up with a new cyclodehydration method where we use zeolites to form the ambrox that we require. And we've actually patented this whole route. Now, if we look at the first step, so the production of the intermediate diol, so going from the sclareol to the diol, what we did was we screened a couple of, or quite a number of soil samples and microorganisms. Some of them from the CSIR library that we have there. We developed some GC methods to follow the reaction, just the normal formation of the sclareol and the ambrafuran, but we've also checked the chirality on the chiral column. We then optimized this hyphozymer rosio-niger bioconversion step. So we initially had to look at the best media compositions just to grow the hyphozymer, and then we looked at the bioconversion step. We found that we grow the bioorganism at 25 degrees Celsius, but we have to do the bioconversion at 20 degrees Celsius to avoid any byproducts from forming. We optimized the substrate concentration. We also looked at the addition of surfactants because scleral is not water soluble. And we also looked at induction of activity using low concentrations of the substrate initially before we add larger amounts of the substrate for bioconversion. We found that if we use relatively low concentrations of substrate, 10 grams per liter, we do get full conversion. And then for productivity, we actually started increasing the scleral concentration, and we found that we can get to 75% yield if we add 50 grams per liter of scleral, but the scleral remaining can be very easily separated from this diol that is the intermediate product. Like I said, unwanted products start forming if we go with at temperatures over 25 degrees Celsius. So we can easily control it by just doing it at 20 degrees Celsius. And interesting, the product is also insoluble in the fermentation broth, and we found that we can therefore separate it very easily from your fermentation broth, and we have a very simple DSP. Now, step 2 is the cyclodehydration, where we go from the diol to the final product. So initially we tested seeing if the chemical cyclizations, and then we've identified a zeolite called CBB100, and this zeolite had to be activated. So we bought the inactive in a white type zeolite from Zeolite International, and we activated with ammonium nitrate, refluxing it for 24 hours and drying it and washing it. Then we reflux with calcium nitride, again filter, wash and dry, and then we activate it under vacuum at 500 degrees Celsius at the local university. But this was quite cumbersome to do that every time, and then we found that we can actually activate it in a household microwave. So you can activate 50 grams of zeolite at 70% power within 15 minutes. Then with time, we actually found that Zeolite International had already activated form of the CBB100, and I call it CBB320, and we then used that, but we still had to activate it at 500 degrees or in the microwave. And this CBB320, we had to use 6 of the zeolites for one of the substrates for the diol, which is used then to convert to the ambrafuran. And then with time, we actually found a new zeolite, CFG, and this one did not require any activation at high temperatures or the microwave, and we used the ratio of 3:1. And the reaction takes place at 25 to 60 degrees Celsius, and within 2 to 5 hours, the whole cyclodehydration is completed. We then, through drying and activating at 100 degrees, we can reactivate and reuse this CFG. But then very recently, we actually found a natural zeolite, not a synthetic one, and we can use that one at a 1:1 ratio at 60 degrees, and within 1 hour we get 96% yield of the final product. And then we just get the product through removal of the catalyst via simple filtration and evaporating the solvent, and within a single recrystallization we got the product in a purity of 99.7%. So if we just finally maybe look at the disadvantages of the chemical synthesis versus the advantages of the new process to illustrate the power of biocatalysis, we find that in the chemical process, they used 8 steps, and we only used 2 steps in the new process. The overall yield was no more than 60%. Our overall yield was as high as 90% if we only used 10 grams per liter, but it's still much higher than the chemical process, even if we go to 50 grams per liter. As illustrated, they use very harsh chemicals for the chemical process, while in the green process, we had no harsh chemicals. There was high energy input from 0 degrees and up to well as very high temperatures to achieve the reactions. With our process, the diol formation, we get the growth at 25 and the bioconversion at 20 degrees, and then the cyclodehydration can be done between 25 and 60 degrees Celsius for 2 to 5 hours. In the chemical process, you needed to dispose some of the chemicals in a special manner. We had no chemicals or waste streams that was a danger or needed special disposal. I mean, even the growth media, you just autoclave it, and then you can put it down the normal sewage system. The heptane that we use for the cyclodehydration as solvent is recycled, so there was no waste there. And with the chemical process, as indicated, there might be a number of health issues, especially on scale-up, while our new process had no detrimental health problems, and we patented this process. So my colleague and I looked at the GC analysis, GCMS, and also LCMS and NMR results of some of the intermediate products that form, but at very small quantities. So it's really difficult to really come up with a mechanism for what's going on in this microorganism. So we just proposed that we found this compound 4, which is a pyranol, and based on that, we actually think that number 2, so the stariol is based basically under the action of the cytochrome P450 enzymes, all the monoamine cyclicized to the lactol. Then another oxidation takes place under Norrish type 1 conditions, and you form the acetate. And it was really, you can definitely smell the acetate or the acetic acid in the process, and which is then again hydrolyzed either chemically or under lipase conditions. In the microorganism to give you the diol intermediate product. This whole consumer to get this conversion. So I just want to acknowledge that we got some funding from CSIR, as well as the commercial partners like Tubes Africa and some other funders like the DSI, which is the Department of Science and Innovation in South Africa, and also other researchers who contributed to the project over the years. This project has resulted in a patent as well as 2 technology demonstrators, the last one at the technology readiness level of 8, and is now ready for commercialization. Thank you very much for your attention, and it's a privilege to present to you.
Thank you, Dr. Lucia, for your presentation. Is anyone having any questions? I think there are no questions from anyone. Thank you once again for your presence and presentation.
Okay, good. It's a pleasure.
Okay.
Thank you.
Thank you. So our next presenter is Dr. Eleftherios Tolupkes from National Research Council, Italy. Hello, Dr. Eleftherios. Are you ready with your presentation?
Yes, hello, I'm ready.
Okay. Yes. You can share your screen with us. Start your presentation.
Yes.
Yes.
So, do you see everything?
Yes.
Okay. Thanks. Okay. Good morning, everyone. First, I would like to thank the organizer for the invitation to this conference. My name is Eleftherios Touloupakis, and I work as a researcher at the Research Institute on Terrestrial Ecosystems of the National Research Council in Florence, in Italy. I welcome you on my talk on purple bacteria as a source of biohydrogen and bioplastics. In this presentation, I will present some experimental data from my group on the growth of photosynthetic bacteria and hydrogen and polyhydroxybutyrate bioplastic production in different types of photobioreactors. I will do a small introduction on photosynthetic macroorganisms and photosynthesis in general. Photosynthesis is the process by which photosynthetic organisms use sunlight, water, and carbon dioxide to create oxygen and energy in the form of sugar. Photosynthetic macroorganisms such as microalgae, cyanobacteria, and purple bacteria are considered future biological resources since they can be used to produce high-value products, biomass, and bioenergy. They have several advantages since they have minimal nutrition requirements. They are a natural source of nutrients, pigments, vitamins. They are rich in minerals. Also contain large amount of structural biopolymers, proteins, and carbohydrates. More specifically, cyanobacteria are able to combine photosynthesis with polyhydroxyalkanoates production and biohydrogen production. Photosynthetic bacteria are able to produce very high, sometimes, quantities of polyhydroxyalkanoates and hydrogen. Polyhydroxyalkanoates approximately 150 different types. They are inert, water-soluble, non-toxic polyesters produced by various microorganisms. They are bio. They present good thermoplastic and mechanical properties. They present excellent biodegradability in various ecosystems. They are, of course, promising candidates for the production of bioplastic items. But they present some disadvantages. The main is the high production cost. High cost is the combined result of the high energy demand for media sterilization, the cost of the carbon source, and the downstream processes. In order to reduce this cost, this high production cost, we must use inexpensive carbon sources such as food waste, plant oils, etc. We must use efficient producers such as photosynthetic no-sulfur bacteria, and we should use efficient culture systems and culture conditions. Biohydrogen, hydrogen is extensively proposed as a future source of alternative clean energy due to its physical and chemical properties. The photosynthetic hydrogen production is achieved with two different light-dependent processes, water photolysis in cyanobacteria and green algae, and photofermentation and the photosynthetic bacteria. Photofermentation is the microbial and anaerobic catabolism of organic substrates to hydrogen carried out by photosynthetic bacteria. In this case, hydrogen is generated during nitrogen fixation as a product of the nitrogenase enzyme. As I told you, optimization of growth conditions such as physical, for example, light intensity, temperature, pH value, and chemical, like growth media composition, will increase the hydrogen production rate. So, Photosynthetic bacteria are widely used as a model organism in macrobiology. They can grow as photoautotrophs, photoheterotrophs, or chemoheterotrophs, depending on the availability of light, carbon, and oxygen. They can produce polyhydroxyalkanoates via photofermentation. They can accumulate intracellular PHA as carbon storage material under stress conditions. PHA productivity depends on the bacterial strain and mainly the growth conditions, such as nutrient deficiency, carbon to nitrogen ratio, and the pH value. So the deployment of photosynthetic microorganisms or, of course, photosynthetic bacteria as a reservoir of bioproducts requires the use of efficient bioreactors, culture systems, in this case, photobioreactors. Photobioreactor is a bioreactor that utilizes a light source to cultivate photosynthetic microorganisms. They are open and closed photobioreactors. Closed photobioreactors are preferred because they provide optimal growth and minimize the risk of culture contamination. In our laboratory, we mostly work with tubular photobioreactors. Tubular photobioreactors contain one or more transparent tubes made from glass or plastic. They are relatively cheap with a large illumination surface area. Tubes can be arranged in various configurations and orientation, of course. Aeration, mixing, and circulation of the culture are done with pumps or airlift systems. The culture productivity is dependent on the number of tubes, their diameter, the biomass concentration, photobioreactor orientation, and location. One of the most used photobioreactor in our laboratory is this cylindrical closed photobioreactor. In the scheme, we can see how the setup of this photobioreactor. There is a magnetic steerer in order to move the rotor and mix the culture. Lamps, of course, the heating cold finger in order to maintain constant temperature, some probes, pH probe, redox probe, temperature probe. There are some sample ports in order to take the samples, the rotor, of course, and a refrigerated heating circulator, and a control unit where all these the data, such as pH values, redox temperature, are registered. So I will show some recent works about PHP and hydrogen production by photosynthetic microorganisms, specifically photosynthetic bacteria. In the first work, PHP and hydrogen accumulation were investigated by culturing Rhodopseudomonas with 3 carbon substrates, acetate, butyrate, or lactate, and using 2 nitrogen sources, either ammonium or glutamate. In this system, in all experiments, hydrogen was determined by using the water column displacement method and by gas chromatography. PHB was determined by HPLC chromatography. So in this work, the results showed that PHB accumulation was higher when butyrate and ammonium chloride were used, about 12% of cell dry weight, and the hydrogen production was higher when acetate was used and glutamate as nitrogen source. We got 1,231 milliliters per liter of culture hydrogen in this experiment. In the next work, the effects of temperature, pH, salinity on PHB synthesis by culturing rhodophyllum sulfidophyllum we studied. Of course, even in this work, PHB production with this marine bacterium was done in a 4-liter photobioreactor, in the same 4-liter bioreactor. And the results showed that when with 4.5 medium salinity gave the best stress growth, was the best stress growth condition to reach the highest PHB concentration. We got 33% of cell dry weight in this work. In the next work, we studied the PHB production and the biohydrogen production by Rhodopseudomonas using different carbon sources are substrate. We tested acetate, succinate, and malate. And we studied the effect on PHB and hydrogen production by this photosynthetic bacterium. Results showed that acetate was the best carbon source since it presents the highest hydrogen production. This, in this case, was 2.2 liters per liter of culture. Also presented the highest PHB accumulation, about 18.3% of cell dry weight. In this work, the next work, whey and molasses were used as inexpensive raw materials for the parallel production of PHB and biohydrogen. Whey and molasses are important bioproducts, very rich in nutrients that lactic acid bacteria can convert in dark fermented effluents, and these effluents are proper media for culturing the photosynthetic bacteria. There are two stages. At the stage 1, lactobacillus convert the agroindustrial byproducts, whey and molasses, in lactate-rich effluents. At stage 2, Rhodopseudomonas cells use the lactate-rich effluent to produce biomass with high content of PHB. Of course, to produce also hydrogen. The results showed that by using 25% of diluted dark fermented whey, a PHB accumulation of 18% of cell dry weight was obtained, while by using 20% of diluted dark fermented molasses, the PHB accumulation was 38% of cell dry weight. The highest hydrogen production rate was about 4.5 milliliters per liter per hour when feeding the bacterium with 30% of diluted dark fermented effluent of molasses. And the next work, again, a cheese whey bioproduct was utilized as a natural feedstock in a two-stage process. Again, at stage 1, lactobacillus cells converted cheese whey in lactate-rich effluent. And at stage 2, the marine bacterium, Rhodophyllum sulfidophyllum, use this effluent to produce biomasses with high content of PHB. The results showed that by feeding rhodophyllum with diluted 50% cheese whey fermenting effluent, the highest PHB content was observed. This was very, very high. About 67% of cell dry weight was polyhydroxybutyrate. So, in the next work, the ability of the marine bacterium Rhodovulum sulfidophyllum to convert single carbon sources, acetate, lactate, malate, and succinate into PHB is evaluated. In this work, the highest PHB content, 39% of cell dry weight, was reached after 1,200 hours of culture growth in presence of lactate under a semi-continuous regimen. So it is very important for market reason to scale up the hydrogen and the PHB production process. Thus, we tend to scale up the photosynthetic bacteria cultures by transferring them outdoors in bigger photobioreactors. Here at the CNR of the Flores area, we have two tubular photobioreactors with capacity of 53 liters and 70 liters respectively. So we have done some experiments outdoors. In the first experiments, we used Rhodopseudomonas palustris. The growth medium was vanille with butyrate and glutamate as carbon and nitrogen source respectively. And in the first experiment, we had a PHB productivity of 45.6 milligram per liter per day. And the next experiment, always we used Rhodopseudomonas palustris. The growth media was vanille with carbon to nitrogen ratio 5 plus sodium acetate and ammonium chloride and yeast extract. In this case, we tested the hydrogen production. The maximum hydrogen production rate was 9.81 liters of hydrogen per liter of culture per day. So we tested, of course, the second photobioreactor, the 70-liter photobioreactor. The aim of this study was the evaluation of the performance of this photobioreactor in terms of biomass growth and polyhydroxybutyrate accumulation under the solar light condition. We used Rhodopseudomonas, and in this case, after several days of growth, the cumulative PHB concentration using lactate as carbon source was 377 milligram per liter for fed batch growth and 255 milligrams per liter for a semi-continuous regimen. So this is it. Thank you for your attention. If you have questions, I'm here.
Thank you, Dr. Eleftherios, for your presentation. Is anyone having any questions? Okay, no questions from anyone. Thank you once again for your presence and presentation. Yes, thank you very much. So our next presenter is Dr. Tatiana Zuck from Justus Liebig University, Gießen, Germany. Hello, Dr. Tatiana. Are you ready with your presentation?
Hello, do you hear me?
Yes.
Okay,
you can share your screen with us.
Screen. Mm-hmm.
Yes, your screen is visible to us.
Okay. Do you see my presentation? Yeah.
Yes, you can start your presentation.
Okay, thank you. So, hello, dear colleagues. First of all, I would like to thank the organizer for their invitation and possibility to present the results of my current project. Today, I am going to talk about preparative redox transformations of carbonyl compounds catalyzed by the white rot fungi. And let's start. Oh. So, I don't understand how to go to the next slide. Uh-oh. Oh, yes. So, firstly, several words about white rot basidiomycetes fungi. Usually, we used to go to the forest and collect mushrooms without any thoughts what they are exactly. And this could be fruiting bodies of basidiomycetes fungi. And why I focused on this organism? Because they are able to generate a unique set of enzymes, namely macases, lignin peroxidases, manganese peroxidases, different oxidoreductases, oxidases, and so on. And these enzymes are able to degrade the most abundant aromatic biopolymers of the earth, namely lignin, that was mentioned in several topics today. Lignin is complex three-dimensional structure polymer, and it's a non-regular polymer. So its degradation is quite a challenging process. Here you can see an approximate scheme how the degradation of lignin can be proceed among different transformation. You can see here the cleavage of carbon-carbon bonds, or oxidation of phenyl hydroxyl to phenoxy radical, or oxidation of alcohol to carbonyl, and the back reduction here. After extracellular degradation of the whole big polymer into low molecular fragments, intracellular biotransformation proceed. And by the way, today the enzymes that are responsible for intracellular biotransformation of low molecular weight lignin fragments are under intensive studies. These enzymes are reach big interest and have been applied for different transformations of various organic compounds. It was found that basidiomycetes enzymes can oxidize alkane to alcohols, and also alcohols to carboxylic acids, and also alkene to epoxides, sulfide to sulfoxides, and these enzymes are able even oxidize aromatic carbon hydrogen bond with phenol formations, and also allylic. They're able to perform allylic and benzylic oxidation. All these transformations are characterized by high selectivity and low toxicity, and they are quite cheap. But the most disadvantage of them are scaling, because mostly biotransformations with basidiomycetes fungal enzymes have been performed only on analytical level. This means micrograms and so on. So preparative potential is not disclosed yet. Among several biotransformations that have been performed on at least microgram level, there are allelic oxidation of valencen with lyophilized mycelium of pleurotus sapidus, and also biotransformations of dimethylamide P with the growing culture of Basidiomycete irbex consort. Here you can see the free products, so allelic oxidation, oxidation of thiophenerine, and also sulfur oxidation with obtaining of such product M1. My collaboration with Gießen University was started from the small project on oxidation of quite untypical substrate for fungi, namely adamantane. Adamantane is saturated H hydrocarbons and contain only saturated CH bonds here. And after screening of 30 species, fungus Tihamidus albidofuscus has been chosen for preparative transformations, and the yield was 39% of corresponding alcohol. Also, we performed the positional selectivity calculation and kinetic isotopic effect experiment, and the results clearly show that hydroxy radicals can be excluded from the CH activation step, and with high probability metal oxide species are responsible for it. Then we apply our approach for toluene, that is a common feedstock in industry, and this molecule include aliphatic and aromatic fragments. As a result, we found a set of products: benzaldehyde, benzylic alcohol, and phenol. And after numerous attempts, the highest yield of whole mixture of products was no more than 20%. We suppose that it could be due to the evaporation of our starting compound toluene from the surface of submerged cultures. And then we decided to check what will happen if we supplemented our culture with benzaldehyde and benzylic alcohol. The block scheme of our approach is presented here. So we did not add our compound directly on the 0 day of culture growing. We waited several days and then added our model compounds. And then after 3-4 days, we worked with the reaction mixture. We found that young cultures, young fungal cultures, display high reductive activity, and with when they grow more days, the oxidation started to dominate. As oxidative processes are already known for Vitroid Basidiomycetes fungi, we firstly focused on reductions, especially due to the fact that hydride-containing agents traditionally employed for reducing of carbonyls currently rise increasing environmental concerns. And alternative catalytic hydrogenations in traditional organic chemistry require heavy metal-based catalysts and often harsh reaction conditions. So we need to find more environmentally friendly approaches. For studying scope and limitations of reduction with dihamidosylbidofuscus, a number of substituted aromatic and aliphatic aldehydes were supplemented to its submerged cultures as we made for benzaldehyde. Here's a general scheme of our transformation, and here you can see the products and corresponding preparative yields. Only I would like to mention that in the case of compound 12, initial aldehyde has the additional double bond in alpha position to carbonyl group, and both of them were reduced. So, in many cases, you can see that yields are quite high, especially in the case of linear aliphatic carbonyls. And we conclude the outstanding selectivity based on NMR analysis of crude extracts from the reaction mixture. So here you can see the NMR of reaction mixture before column separation. And the signals of target products clearly dominate and agreed well with the spectral data of the corresponding standard samples. So, the next step, we decided to apply our approach for carboxylic acids. The reduction of carboxylic acids to the respective alcohols usually requires either prolonged heating with large amounts of hydride reagents or involvement of heavy metal-based catalysts. With our fungi, dihamidosylbidofuscus, benzylic acid was readily reduced to corresponding alcohol, benzylic alcohol with high yield, and it was performed with the young culture to this older dihamidosylbidofuscus culture. And then we tested the transformation with more old culture. We did not find any traces of alcohol in the media, but only benzylic carbon, benzaldehyde with a 45% yield. And it's quite promising approach because it's difficult to reduce carboxylic acids to aldehyde. And usually in industry, this product can be obtained like result of hydrolysis of the halogen derivative. So, nitro substituted benzylic acid were reduced to the corresponding alcohols with high yield. You can see it here. And nitro group remained unchanged during transformations. That is also unusual for traditional organic chemistry. And among substituted benzylic acid, we tested also vanillic acid that has been reduced to the vanillin, but the yield was not very high. Also, we tested our transformation for cinnamic acid and some of its derivatives. In the case of cinnamic acids, only traces of product of reduction were found in reaction mixture, but both other derivatives were reduced with high yields. So we can see that This approach also can be used for reduction of carboxylic acid. Also, we again decided to test adamantane, but in this time with carbonyl group. We decided to test the reduction process of carbonyl group versus oxidation, possible oxidation of carbon hydrogen bonds of this saturated cage. And the biotransformation gave the alcohol with high preparative yield, but traces of desubstituted derivatives of adamantane, which accumulated at prolonged reaction times, were detected also in reaction mixture. So you can see here that after 4 days of biotransformation, this compound has been isolated with a 71% preparative yield, but then the yield is decreased and the products of deep oxidation accumulate. Then we decided to check other basidiomycetes fungi for the property to reduce of carbonyl groups because we were not sure is it a unique property only of Dichamatus albidofuscus, or maybe other fungi are also able to do this. And as model compounds for this experiment, we choose again benzaldehyde, then substituted benzaldehyde with the nitro group. We would like to test it due to this electron withdrawing nature of substituent. And also we decided to test two saturated ketones that are quite untypical for fungi. We apply here almost the same procedure as the first time, and this is a list of fungi that we tested. Here you can see the screening results, and our initial compound in every case is in red color, and the product of reduction is in green. And you can see that almost all fungi can reduce carbonyl group. The only fungus that did not show any traces of products of reductions is Pleurotus ostreatus. Also, it should be mentioned that results for every model compound were quite different. If we compare, for example, benzaldehyde and the paranitrobenzaldehyde, we can see that in the case of first compound, in many cases, were found also we have found also benzylic acid as a product. So together with the reduction, oxidation proceed. But in the case of substituted benzaldehyde, no product of oxidations have been detected with all these fungi. Only Dichamatus squalene and Dichamatus albidofuscus show only oxidative activity here. In the case of saturated ketones, also there are some difference because cyclohexanone has been only reduced to corresponding alcohol, but adamantanone also has been oxidized to desubstituted derivatives by at least 4 fungus. And especially in the case of Marasmius cohortalis, only products of oxidation has been detected in the reaction mixture. So we can say that screening of 9 basidiomycetes fungi displays superior efficiency of some of them for reduction of carbonyl aromatic and aliphatic derivatives. And we show the preparative potential of whole cell culture of Dihanitis epidophysus for on water reductions. And with this fungus, we performed many biotransformations on the preparative level. So also I would like to thank organizations that support the current project. This is German Academic Exchange Service, Alexander von Humboldt Foundation, my home university, Kiev Polytechnic University of Ukraine, and my host university, Justus Liebig University. Also, big thanks to Professor Holger Zorn, in which group I am working at the moment, and my colleagues that helped me a lot, as I am actually a pure organic chemist, and these biotransformations are quite new for me, but this kind colleagues introduced me to this biological approach. Thank you very much for your attention.
Thank you, Dr. Tatiana, for your presentation. Is anyone having any questions? Okay, no questions from anyone. Thank you once again for your presence and presentation.
Thank you.
Okay, so our next presenter is Dr. Wusheng Wu from Georgia Institute of Technology, USA. Hello, Dr. Wusheng. Are you ready with your presentation?
Yeah, I'm ready.
Okay, you are the presenter now. Please share your screen with us.
Okay, can you see that?
Yes.
Okay.
Okay, you can start your presentation.
Hold on, let me. I need to make this smaller, so okay, got it. All right, so hello everybody. This is my pleasure to be invited to the webinar of Chemistry and Applied Chemistry 2021. I wasn't noticed that like there are so many of you are green chemistry and total synthesis chemistry and catalyst professionals. This, I think I am the first and the very few of you as the medicinal chemist. So I'm gonna share my research with you as a, hold on, I try to make the meeting window smaller because it blocks my presentation. I try my best to. Okay. So today my topic is novel HDAC inhibitor to suppress the liver cancer tumor growth, and this is the work I led, and my PI is Dr. Oyeleri in Georgia Tech, and we are in the Department of Chemistry and Biochemistry. So first of all, let me give you an introduction of the HCC. So HCC is, in the other name is hepatocyte carcinoma, and this is the most common and most severe type of the liver cancer, which is also the most popular type of the liver cancer. It's more than 80% of the patients has this problem. The HCC is induced by the alcohol, virus infection, smoking, genetic deficiency. So in most of the case, there were the long-term inflammation, and that can cause the cirrhosis of the liver. And when the cirrhosis gets more intense, it will induce to the hepatocellular carcinoma, which is the most severe type of liver cancer. And this cancer is really low in the 5-year survival rate current days. It's only about 18%, and it has very poor prognosis, which means when the patient diagnosed with the HCC, it's been the middle or the late stage, and that makes this cancer to be one of the leading lethal cancer in the world. There are several treatments for the liver cancer, HCC. Nowadays, there are 3 major types of methods. The first method is surgery, and the second one is chemotherapy, and the third one is immunotherapy. For the surgery, unfortunately, even though it's applicable for patients with early stage and middle stage, however, many of them that had the surgery, 60% of the patient has the relapse. So, and also the chemotherapy has its limit to the HCC as well. The sorafenib, which is one of the major standard care of the HCC, is not efficient to the patients. It only extends in average 1 to 3 months of the patient life. So nowadays, one of the promising therapy, as known as anti-PD-1 immunotherapy, is able to cure the cancer for some of the case. However, for most of the case, the patients are not responding to the anti-PD-1 inhibitors because the immune system is not recognizing it's not using the PD-1 to kill the cancer. So that was not really applied to all of the patients, only 30%. So this is all the information of the HCC. And now what we focus on is the epigenetic side of the HCC. So epigenetic side, the HDACs are playing very important role for the HCC. The HDACs, in the other name, histone deacetylase, can prevent the tumor suppressor expression, and especially the HDAC class 1 isoform, which is the HDAC 1, 2, and 3. They are highly expressed in the HCC. And the HDAC isoform, HDAC 1 and 2, strongly associate with HCC cell proliferation, while the HDAC 3 is regulating it with HCC stem cell renewal. So the cancer stem cells are usually maintaining the cell's survival and also the over proliferation. So this is also important. And researchers has found that induction of the malignancy in HCC is highly related to the HDAC isoform 1 expression, and that in those patients with HDAC highly expression, high expression can also related to the high death rates. So what we want to do is we need to block we try to block the HDAC isoform 1 only to see if that will benefit the efficacy. So first of all, this is the picture here, which is the HDAC mechanism. If you are not very familiar with the HDAC mechanism, I can explain a little bit through this picture. So HDACs, they are controlling the DNA transcription because the histone here with the sphere, they are wrapping up the chromatins, and the chromatins has the DNA is wrapped up. And in those cases, the histone is having the electrostatic force with the backbone of the DNA phosphate group. So it's wrapped tightly, and so the DNA is not able to expand and being transcribed. However, HAT, by using the HAT histone, the transferase, the histone is able to open up the DNA because the electrostatic bonding is broken by the acetylation here on the amine group. So the HDAC itself is to close the DNA and not let them transcribe. So many of the tumor suppressors are not be able to be expressed under the HDAC effect. So the HDACs are overexpressed in many cancers, and that will silence the guardian protein, so that signal of the cell death or apoptosis is being silent, so then the cells can overgrow. So that is the idea why we are using HDAC inhibitor, is to regulate back the normal function of the cells, so the cells can die or induce apoptosis afterwards. And so that could give us a purpose of anti-cancer. So then HDAC inhibitors has been studied for decades. Many of the HDACs has been published or approved by FDA. So the SAHA here is one of the standard HDAC inhibitor. The balinostat, chitamide, and romidepsin, and panobinostat. And those compounds are very, they have the common problem as they are not able to penetrate into the solid tumor, and they also have the off-target effects, which means they lack of efficacy to the solid tumor treatment, and then only works for the hematopoiesis disease like the leukemia and those kinds of blood cancer disease. So our solution here is to give the HDAC inhibitors a solid tumor penetration, while it will have the HDAC isoform 1 selectivity. So that's what we had in the previous study. We introduced the macrolide as a moiety to link with the zinc binding group here. This hydrosomate is the zinc binding group that will block the zinc in the HDAC. So then the HDAC is not able to function and induce any deacetylation in the DNA over here. So this will have the deacetylation. So then the bond here will be broken. So that's how the hydrosomate should work. So what we expect to see is that this compound that has the macrolide moiety is able to help us to bring our hydrosomate into liver and the lung, because macrolides are accumulating in lung and liver. So we want this area to only be the tissue selective moiety that can navigate our compound to the right target. So then we put this compound into the HDACs assay, and we find out that this assay is telling me that this HDAC inhibitor here is not showing the isoform 1 selectivity, but it blocks a lot of HDACs. It's the broad spectrum HDAC inhibitor, which we thought will be good, but afterwards when we test them into the cells, it doesn't show very good results. I will show you later. Then we are thinking, how do we getting this hydrosomate group into a isoform 1 selective? So we introduced the benzamide compounds. So those benzamide compounds has this 2 area that is chelating with the chelating with the zinc, could also be a zinc binding group. So we introduced the thiophene, the floral of the benzamide. And because this group is known as the HDAC isoform 1 selective zinc binding group, so we replace the hydrosomate with those groups. And we hope that this compound will give us not just the liver tissue selectivity, but also the HDAC isoform 1 selectivity. So this is the straightforward synthesis because we have prepared all those in the lab. What we need to do is to have a EDCI coupling between the benzamide here with the acid group here. So then we have this whole linker with the azido group. So we do the click reaction with the prepared modified macrolide here. And so that is giving us the compound 2. And in the same methods with the floral group, we are able to make the 3A and B. And those two, after the synthesis, we test them into the HDAC assay kit, and we find out that those compounds, even though it has a very poor IC50 because the benzamide group is too bulky, sometimes it's not really able to bring into the pocket efficiently, but it does help us to block out all the other HDAC inhibitions. Only works on the HDAC 1, 2, and 3. So we put them into the Western blot to reconfirm the HDAC inhibition. As alpha tubulin, which is controlled by HDAC 6, is no longer able to be getting acetylated in treatment of 3A or compound 2, only in the SAHA. But H4 is upregulated in 3A and 2, both works very well. And that tells us that those compounds are able to acetylate H4, which is controlled by the HDAC isoform 1. But not working on the alpha tubulin, which is controlled by HDAC 6. So this Western blot matches what we saw in the cell-free assay here. So in the cell-free and cell-based assays, we all confirmed this compound is selective to the HDAC isoform 1. So then we test this group, compounds into all types of HCC cell lines with to see the anti-proliferation rate compare with the Kupfer, which is the normal liver cell. And we compare the compound 1 with the 2 and 3A. And even though the compound 1 has the broad spectrum HDAC inhibition, it doesn't really work very well to kill those cell lines, only kills the HEP3B. But as long as you can see the compound 2 and 3A, they are showing excellent IC50 data in all those HCC cell lines comparing to the Kupfer cell line. This is about more than 30 times or 30-fold selective index to the normal liver cell. So this is telling me that these compounds are working excellent, and they are trying to just targeting to the HCC cell lines instead of normal cell. So we compare we compare with the SAHA to see whether those compounds can induce the apoptosis, because usually HDAC inhibitors will induce the cell apoptosis, as I mentioned before, and we see the upregulation of the P21. The P21 upregulation is to induce the cell apoptosis, and we also see the cleavage of the caspase 3, which is another evidence for cell apoptosis. So those two are telling me this compound is the 3A and 2. They are all doing the right job. They are killing cells by inducing the apoptosis, and this is classic to all the HDAC inhibitors. And we also see that our compounds is inducing the G1, G0 phase of the cell cycle arrest, and doing not very obvious effects on the other two cycle stages. So this is information that this drug is doing G1 phase arrest with the cell apoptosis. So the mechanism of the cell death is known right now. So what we need to do right now is to see whether this drug that is doing well in the in vitro test will also show a very strong tumor suppression level in the mice model. So we inject the mice with the very high dosage with 25 and 50 milligram per kilogram to get the MTD data. So MTD data is to telling us if the drug has any toxicity that can induce the mice weight loss. And we don't see any weight loss in any of the mice here, even though we are inputting the 50 milligram per kilogram dosage. So that tells us these compounds 3A and 2, they are not super toxic to the mice, and they are not inducing any weight loss or side effects. So then we test them, we inject them into the tumor, tumor-induced mice, comparing with the DMSO and the compound with the sorafenib group. We see that the compound 2 is actually doing exactly the same as the sorafenib, and this is a promising tumor suppression level, which is not inducing any toxicity, because chemotherapy and the sorafenib, they are always inducing weight drop in the high dosage, but our compound seems to be very safe and also doing very strong level of the tumor growth after we measure it. So this is a evidence of the tumor suppression. So we, as I mentioned before, HDAC inhibitors, they always have the problem in penetration of the solid tumor. So we need to test our compounds whether they can penetrate the tumor, and we find out in the tumor, the compound is being uptaken by the tumor, and this is the very high picogram dosage level in the tumor. And this is a evidence that the compound 3A is able to penetrate tumor very well. And we also, because we induce the macrolide in this compound, so we expect to see the liver accumulation of this compound because macrolide itself is able to get into the liver very quickly and accumulatively. So we see this evidence as well. That tells us our compound is not just showing very selective HDAC inhibition on the isoform 1, but it also induces the cell death, HCC cell death, and also tumor suppression with no significant weight loss on the mice. And on the other side, it goes to the liver, which is tissue targeting, and also tumor, which is very good penetration rates in the solid tumor. So all those give us a very good indication that this compound is actually a very exciting compound that could be further investigated in more preclinical data and see whether it has a potential for the clinical use. So this is the whole presentation for this compound and this project. And this is a excellent work between the teamworks with Dr. Oyelere, Dr. Tabata Subasic, and Dr. John Petrosing from Emory. And this is my email. I have done multiple disease drug discovery, including idiopathic pulmonary fibrosis, triple negative breast cancer, and hepatocyte carcinomas. And our lab is not just focusing on epigenetic regulation inhibition, but also have a lot of tissue targeting, cell type targeting, anti-cancer and anti-inflammatory drug. So that's everything I have right now today. Thank you for your attention.
Thank you, Dr. Bosheng, for your presentation. Is anyone having any questions? Okay, no questions from anyone. Thank you once again for your presence and presentation.
Thank you so much.
Okay, and today's last presentation is from Dr. Ehlam Ben Khalifa from University of Tlemcen, Algeria. Hello, Dr. Ehlam. Are you ready with your presentation?
Yes, I'm ready. So I
Okay.
will share with you my screen.
Yes.
So it's visible now?
No. Yes, now it's visible.
Okay.
Okay, please start your presentation.
Hello everyone. My name is Ben Khalifa Ahlam. I'm PhD student in University of Tlemcen, Algeria. First, I would like to thank the organizer of this interesting conference. Thank you very much for this amazing opportunity and your hard work. So my presentation is titled Swelling Kinetics and Thermal Behavior of Hydrogel composed of N-butyl acrylate and isobornyl acrylate. My presentation is divided in 5 parts. I will start by introduction. Next, I will present my literature review, material and methods, experiments and results, and finally, I will finish by conclusion. So many researchers have studied the science of polymer gel. This is due to the potential application of this kind of polymer systems. The attention was to focus in the innovation and development of new materials for this system. So the major shortcoming of this kind of polymer network is their poor mechanical properties when they are in the swollen state. The increasing in the cross-link density and copolymerization with a more resistant system are among the ways to reinforce this system, as well as the formation of interpenetrating polymer network IPN. So what is an IPN or interpenetrating polymer network? An IPN, known as the blend of at least 2 polymers in a network form, one of them is synthesized or cross-link in the immediate presence of the others. The synthesis of this new material class make it possible to have, in certain cases, new materials with the good performances in comparison with the initial polymer precursors. Generally, this polymer network are synthesized by any known method of polymer synthesis. The most used approach for the synthesis of IPNs are: first, polymer network 1 is synthesized, then the second monomer plus crosslinker and activator are swollen into network, and polymerized in situ. The resulting IPN is called sequential IPN. In the second case, the monomer or homopolymer plus crosslinker and activator of both components are mixed, followed by simultaneous polymerization. Typical syntheses involve chain and step polymerization kinetics. So in order to use interpenetrating polymer network for practical application, it is required to understand the different properties of this polymer network. In this work, a novel sequential IPN based on butyl acrylate, a very useful monomer for several industrial application, and the isobornyl acrylate as a hard polymer. View of their complementary properties, blending isobornyl acrylate and butyl acrylate is a natural choice to improve property, including rigidity. So, 2 kinds of IPN were synthesized. The first one consists of a butyl acrylate network swollen until reaching equilibrium in a solution containing the second monomer, plus crosslinker and photoinitiator. The swollen sample was then exposed to UV irradiation. Generally, the exposure time was fixed to 13 minutes to achieve complete conversion of all the monomers in the precursor system. The resulting network will be called IPN1. The second IPN was obtained with the same method described above, except that a first of polybutyl acrylate network was formed, which was swollen in second step until reaching equilibrium by a solution containing polyisobonyl acrylate. So infrared analysis, as shown in this figure, the evolution of the conversion rate of acrylate function as function of exposure time to UV irradiation of the precursor monomer mixture isobonyl butyl acrylate HDDA curve. This curve was deduced from the decrease of surface of the absorption band at 810. So as shown in this figure, changes of absorption of the band at 8010 were considered to present the evolution of photopolymerization reaction during UV irradiation. Also shows that an irradiation time of 35 minutes makes it possible to obtain a maximum conversion of the acrylic function around 98%. So the swelling to calculate the swelling ratio, this figure consists of the measure of quantity of the reactive solution absorbed by the two different polymer networks as the time proceeds. The two reactive solutions diffused into network due to the concentration gradient resulting in the exponential swelling of the network form the same swelling curve. It is observed that the two polymer networks have practically a similar physical behavior, that is, say they swell both in the same way and in the same speed. We can also say that the two polymer networks have a maximum swelling ratio around 475 for butyl acrylate network and 288 for isobonyl acrylate. Which means that each network can swell up to 3 times its initial volume. With a small logic, each network contains the equivalent of 3.5 network in addition to the initial networks. The thermal analysis was carried out to know the phase separation behavior that can exist in the different polymer networks. The study focused on the second heating. That is to say, the first cycle of temperature variation of minus 70 to 180. Having obtained a similar curve for the three tests, we present only one curve for each composition. This figure represents the glass transition temperature variation of the different networks. As observed, only one single transition in the DSC curves for all the polymer is detected, especially for the two sensitive IPNs, which indicates that the IPN don't present phase separation. This would suggest that the different network, butyl acrylate and isobonyl acrylate, are perfectly mutable. In addition, this figure informs us that the glass transition temperature of both IPNs are close from to each other and are controlled first by the quantity of the precursor polymer network present in the mixture. And that the TG of the IPN1 show slight shifts compared with the TG of butyl acrylate network. Apparently, with the presence of butyl acrylate in the IPN1 structure, this decrease in TG or glass transition temperature was accepted because in the network 1 equivalent to IPN1, where the presence of the monomer butyl acrylate is governing. This Last tends to influence in the behavior and those to have glass transition temperature more or less close to that of the pure network betyl acrylate. So in conclusion, we can in this work we demonstrate a synthesis of novel sequential antiapiretic polymer network composed of N-butyl acrylates and isobonyl acrylates, and we studied the thermal properties by DSC analysis. The system swelled exponentially to saturation over 48 hours due to concentration gradient. The DSC resetting informed us that the glass transition temperature of this different network studied influenced by the amount of the monomer absorbed by the network. So that's all, and thank you for your attention.
Thank you, Dr. Ahalam, for your presentation. Is anyone having any questions?
Yes.
Yeah, sorry, I have a question, just curiosity.
Okay.
Yeah, thank you for the presentation. I'm just wondering about the possible applications of these polymers.
Okay. For the application, we can use this kind of polymer or IPN in the biomedical application, like the SMART material. Mm-hmm. And this material can present generally a good shape memory. So this is one of application.
Okay, thank you so much.
Thank you.
Thank you for answering the question. Is anyone else having any questions? Okay, no questions from anyone. Thank you once again, Dr. Ahalam, for your presence and presentation.
Thank you.
Okay, so by this we came to end of our day one webinar. I would like to thank all the attendees and participants of today's webinar. Hope you enjoyed the webinar and gained knowledge from the sessions, and request you to attend tomorrow's sessions too. If you have any queries, you can mail to the concerned program manager. Thank you everyone for making the webinar successful.
Goodbye.
Thank you, bye.
Thank you. Goodbye.
Ik kon wel niet lief.